Hello and welcome to The Sleepy Scientist. Tonight's question is a big one, quite possibly the biggest, the Big Bang, and whether there was ever such a thing as before. Before we begin, one honest little moment. As many of you know, this channel runs without ads, so nothing will interrupt you tonight. Keeping it that way takes a little support though, and the best way to help is the ebook. If you have a spare minute, and only if you do, pause here and take a look. There is a QR code on screen throughout the video and a link in the description to the website thesleepyscientist.com. It is a calm, careful guide to quantum physics, the ideas behind the videos given room to breathe, with the full narrated audiobook included. Taking a look really is the single best thing you can do to keep these quiet videos coming. That's the only ask tonight, and it's a heartfelt one. Thank you. Now, let me know where in the world you're watching from. Maybe you're tucked up in bed with the lights low, curled into the corner of a sofa, half listening on a late train, or sitting beside a cup of tea that was definitely warmer a few minutes ago. Wherever this finds you, I hope the room is gentle, the day is slowing down, and your mind has little space to wander. I'll try not to make tonight's question so interesting that it keeps you staring at the ceiling until sunrise. But if that does happen, at least you'll be lying there with a slightly better understanding of why asking what came before the universe is not quite as simple as asking what came before breakfast. Science does like to make the big questions awkward. It's one of its little hobbies. So let's begin, shall we? The Big Bang. Was there a before? And if the Big Bang was not an explosion in space, but the expansion of space itself from an extremely hot, dense early state, then what does the word before even mean when time may be part of the thing being born? People often ask what happened before the Big Bang as though the universe were a story with a missing first page. It feels like a natural question. After all, almost everything in ordinary life has something before it. Before a tree there was a seed. Before a house there was an empty patch of ground, a plan, a builder, and probably at least one person looking at the instructions with quiet suspicion. Before the morning there was the night. Before a sound there was silence. So when we hear that the universe began with the Big Bang, the mind immediately reaches backwards and asks, quite reasonably, what was there before? But this question is stranger than it first appears, because the Big Bang is not simply an event that happened inside time in the usual way. It may be connected to the origin, or at least the earliest known state, of time itself. And that makes the word before much less simple than it feels when we use it in everyday life. The Big Bang is often imagined as a kind of cosmic explosion, a blazing fireball bursting outward into empty darkness, sending galaxies flying like sparks from some unimaginable blast. It is a dramatic picture, and in fairness, it does have a certain cinematic charm. But it is not really what modern cosmology means by the Big Bang. The Big Bang model describes the universe expanding and cooling from an earlier, hotter, denser state. It does not describe matter exploding into pre-existing empty space. It describes space itself expanding. Every large region of the universe was once much closer together. The distances between places were smaller. The temperature was far higher. Matter and radiation were packed into conditions so extreme that atoms, stars, planets, and familiar structures could not yet exist. This is the first important distinction. The Big Bang model is not just a vague creation story with a scientific coat thrown over it. It is a well-supported physical description of the early universe, built from several major lines of evidence. The expansion of the universe, the cosmic microwave background, the abundance of light elements such as hydrogen and helium, and the large-scale structure of galaxies all point toward a universe that was once much hotter and denser than it is now. But that is not exactly the same as saying science has fully explained the absolute origin of everything. The hot Big Bang model tells us that the observable universe has an early history. It tells us that if we follow cosmic expansion backward, the universe becomes hotter, denser, and more uniform. It tells us that the young universe passed through stages where light, matter, and space behaved very differently from the world we know now. But the deeper question of whether this early hot state was the absolute beginning of reality is much more uncertain. This is where many misunderstandings begin. When scientists say the Big Bang happened, they usually mean that the universe expanded from an extremely hot, dense early state. They do not necessarily mean that they have proven what, if anything, caused that state to exist. They do not necessarily mean that there was a single first instant in the way a stopwatch has a first tick, and they do not necessarily mean that the question of what came before has one clear answer. Some models suggest that time itself may have begun, or at least lost its familiar meaning, near the earliest boundary of the universe. In that case, asking what happened before the Big Bang may be a little like asking what is north of the North Pole. The words are understandable, but the direction stops behaving in the ordinary way. Other models suggest that there may have been something before the hot Big Bang phase. Perhaps an earlier contracting universe, an inflationary state, a quantum transition, or some deeper structure that our current theories do not yet fully describe. The honest answer, then, is not a simple yes or no. It is a careful separation between what is strongly supported and what remains open. The strongly supported part is that the universe was once in a hot, dense, expanding state. The uncertain part is whether that state was the true beginning of all space, all time, all matter, and all physical law. That uncertainty is not a weakness of science. It is one of the signs that science is doing its job properly. It marks the boundary between evidence and speculation, between what observations can confirm and what theories are still trying to reach. To explore this question properly, several areas of physics have to come together. Observational cosmology studies the universe as a whole, using telescopes, galaxy surveys, ancient light, and patterns written across enormous distances. General relativity, developed by Albert Einstein, describes gravity not as a simple pulling force, but as the curvature of spacetime. Particle physics studies the smallest known ingredients of matter and the forces acting between them, especially under the extreme energies of the early universe. Quantum gravity, still unfinished, tries to understand what happens when the rules of quantum theory and the rules of gravity must both be applied at once. That last part matters deeply. The earliest universe was not merely hot in the ordinary sense, like a furnace or a star. It was a state where density, energy, gravity, and quantum effects may all have been pushed to extremes beyond direct experiment. Our best-tested theories work beautifully across huge ranges of reality, but near the very beginning, they may be stretched past the point where they can safely answer every question. So the mystery is not whether the Big Bang was real in the broad scientific sense. The evidence for a hot, dense, early universe is very strong. The deeper mystery is whether the Big Bang was the beginning itself, or whether it was only the beginning of the universe as we can currently describe it. That is the quiet tension at the heart of the question. We can trace the universe back through astonishing chapters of cosmic history. Stars, galaxies, atoms, radiation, plasma, and the first light that still fills space today. But when we push further back toward the edge where time, space, gravity, and quantum physics all meet, the path becomes less like a road and more like a shoreline at night. We know there is something there. We can hear the waves, we can see the faint outline of the water, but beyond it, the dark is not empty. It is simply not yet fully mapped. The phrase Big Bang can be a little unhelpful, which is slightly unfortunate, because it is also one of the most famous phrases in all of science. It sounds simple, it sounds dramatic. It sounds as though, once upon a time, all the matter in the universe was packed into one tiny point, sitting inside a vast empty darkness, until suddenly it exploded. Then stars, galaxies, planets, and eventually confused people with blankets and cups of tea were flung outward into the cosmic night. It is a memorable picture. It is also not quite right. The Big Bang model is not the idea that the universe exploded from one particular location into empty space. It is the scientific description of an expanding universe that was once much hotter, much denser, smoother, and more compressed than it is today. It describes a universe whose large-scale history can be traced backward to a state where space itself was smaller in extent. Matter was packed far more closely together, radiation filled everything, and the familiar structures of the modern cosmos had not yet formed. That is the important shift. The Big Bang was not an explosion in space. It was, as far as modern cosmology can tell, an expansion of space. In an ordinary explosion, there is a centre. There is a place where the explosion happens. Material bursts outward into surrounding emptiness. If you could somehow hover safely outside it, preferably with very good protective goggles and a strong sense of regret, you could point toward the middle and say, there it is, that is where it began. But the Big Bang does not work like that. There is no known central point in space where the universe started. Every large region of the observable universe was once closer to every other large region. The distance between places has grown because the fabric of space has expanded. From any galaxy, if you looked out across the cosmos on the larger scales, you would see distant galaxies generally moving away. Not because your galaxy is magically special, but because every observer in the expanding universe sees distant regions receding as the space between them stretches. A common way to picture this is to imagine marks drawn on the surface of a balloon as the balloon inflates. The marks move farther apart not because they are crawling across the rubber, but because the rubber itself is stretching. The analogy is not perfect, because the universe is not literally the surface of the balloon, and there is no need to imagine it expanding into some higher room around it. But it helps capture the main idea. The increasing distance is caused by the stretching of the underlying space. This is why galaxies are not simply flying through a fixed, motionless emptiness like sparks from a bonfire. On smaller scales, gravity holds galaxies, galaxy groups, and galaxy clusters together. The Milky Way is not being stretched apart by cosmic expansion, and neither is the solar system, Earth, your bedroom, or the biscuit you may or may not have brought with you. Local gravity, electromagnetism, and other forces easily overpower expansion on those scales. But across enormous cosmic distances, especially between galaxy clusters, the expansion of space becomes the dominant pattern. The farther away a galaxy is, the more the light from it has usually been stretched during its journey toward us. This stretching is called cosmological redshift, because the wavelength of the light is shifted toward the redder, longer wavelength end of the spectrum. The name Big Bang itself has an interesting history. It was popularized by the astronomer Fred Hoyle, who used the phrase during a radio broadcast in 1949. Hoyle did not support the Big Bang idea. He was associated with the steady-state model, which proposed that the universe had no beginning in time and maintained roughly the same overall appearance as it expanded, with new matter continuously appearing to keep the density steady. The phrase Big Bang was partly a colourful way of referring to the rival theory. Science, being science, then did the rather awkward thing of keeping the catchy name while gradually moving away from the picture the name seems to suggest. The phrase survived, even though the firework image is misleading. This is why it is worth slowing down over the meaning. The Big Bang is not a blast wave travelling through pre-existing darkness. It is the early hot dense condition of the universe, and the expansion that followed. Another useful distinction is between the observable universe and the entire universe. The observable universe is the part of the cosmos from which light has had enough time to reach us since the early universe became transparent. It is not necessarily the whole universe. It is simply the region we can, in principle, observe from our position. The universe is about 13.8 billion years old, according to the best current measurements. But the observable universe is not only 13.8 billion light-years across. That might sound surprising at first. If light has been travelling for 13.8 billion years, it feels natural to imagine a radius of 13.8 billion light-years. But while that light was travelling, space itself was expanding. The regions that emitted some of the oldest light we can see are now much farther away than they were when that light began its journey. Because of this expansion, The observable universe is thought to be roughly 93 billion light-years across. This does not mean anything travelled through space faster than light in the ordinary local sense. It means the space between very distant regions expanded while light moved through it. Relativity allows the stretching of space itself to increase distances on enormous scales in a way that is different from a rocket speeding through its local neighbourhood. This matters deeply for the question of whether there was a before. When people ask what came before the Big Bang, they often imagine rewinding an explosion back to its first spark. But modern cosmology is not simply rewinding flying debris. It is tracing the expansion of space, the cooling of radiation, the formation of matter, and the changing behaviour of the universe itself. So, before the Big Bang usually means before the hot, dense, expanding phase that our evidence points toward. It does not automatically mean before everything existed. That is a much deeper question. The Big Bang model describes an early condition with extraordinary confidence, but it does not by itself settle whether that condition was the absolute beginning of space, time, matter, energy, and physical law. It tells us that our universe was once hotter, denser, and simpler. It tells us that the cosmos has changed. It tells us that the galaxies, stars, planets, and quiet late-night questions came from a universe that has been expanding and cooling for billions of years. But the very first boundary, if there was one, remains more mysterious. The Big Bang is therefore not best imagined as a noise in the dark, or a cosmic firework, or a single point detonating into emptiness. It is better imagined as the earliest well-supported chapter of an expanding universe, a hot, dense beginning to the story we can trace, though perhaps not the final answer to why there is a story at all. For a long time, it felt natural to imagine the universe as something fixed. Stars moved across the night sky, planets wandered against the background of stars, comets appeared, disappeared, and made everyone slightly nervous for understandable historical reasons. But the universe as a whole, the great stage on which everything happened, seemed steady. It was simply there, vast, quiet, ancient, and unmoving in the deepest sense. Then Albert Einstein changed the meaning of gravity. In 1915, Einstein completed the general theory of relativity, one of the most important scientific theories ever developed. In Newton's older picture, gravity was a force acting between masses. Earth pulled on the moon, the sun pulled on Earth. Objects attracted one another across space. It was a remarkably powerful idea, and it still works beautifully for many everyday and astronomical calculations. But general relativity described gravity in a deeper way. In Einstein's theory, massive objects do not simply pull on one another through empty space. Matter and energy shape spacetime itself, and objects follow paths through that curved spacetime. The sun does not tug Earth by an invisible string. Instead, the sun curves the spacetime around it, and Earth moves along a path shaped by that curvature. This was a profound shift. Gravity was no longer just something happening in the universe. Gravity was connected to the structure of the universe, and once space-time itself became part of the physics, the universe became harder to keep still. Einstein's equations allowed space-time to curve, stretch, and evolve, but Einstein, like many scientists of his time, expected the universe as a whole to be static. He imagined a cosmos that might contain moving stars and galaxies, but whose overall large-scale structure stayed the same with time. There was a slight problem. His own equations did not naturally want to sit quietly in that arrangement. Without some extra ingredient, gravity would tend to make a static universe collapse inward. So Einstein added what became known as the cosmological constant, a term that could act against gravity on cosmic scales and hold the universe in balance. It was, in a sense, a mathematical prop to keep the cosmos standing still. The universe, however, had other plans. It is often rude like that. Other physicists soon noticed that Einstein's theory seemed to allow a very different kind of universe. In 1922, the Russian mathematician and physicist Alexander Friedmann, found solutions to the equations of general relativity in which the universe could expand or contract. These were not small local motions, but changes in the scale of the universe itself. Friedmann showed that a dynamic universe was not a mistake in the mathematics. It was a genuine possibility. A few years later, the Belgian priest, physicist and cosmologist Georges Lemaitre reached a similar conclusion. Lemaitre understood that general relativity could describe an expanding universe, and he connected this idea to astronomical observations. He proposed that the universe had once been far denser than it is now. Later, he described the idea of a primeval atom, an early attempt to imagine the universe emerging from an extremely compressed state. That phrase is not used in modern cosmology in the same way, and the details of Lemaitre's picture were not the same as today's Big Bang model. But the underlying insight was extraordinary. If the universe is expanding now, then perhaps it was once smaller, hotter, and more tightly packed. The beginning of cosmic history might not be a calm, eternal stage, but a universe changing with time. At the same time, astronomers were slowly gathering the observations that would make expansion difficult to avoid. One of the key figures was Vesto Slipher, an American astronomer who measured the light from spiral nebulae, the objects we now know as galaxies beyond the Milky Way. Slipher found that many of these objects showed redshift. Their light had been stretched toward a longer, redder wavelengths. At first, this was usually interpreted as motion away from us, although the full cosmological meaning would take more work to understand. Another essential piece came from Henrietta Leavitt. While studying Cepheid variable stars, Leavitt discovered a relationship between how bright these stars truly are and how quickly they pulse. This made Cepheids enormously useful as distance markers. If astronomers could measure a Cepheid's changing brightness, they could estimate its true luminosity, compare that with how bright it appeared from Earth, and work out its distance. This was a quiet revolution in measuring the universe. Without reliable distances, redshifts alone could not reveal the large-scale pattern. The universe needed both a sense of how far away galaxies were and a sense of how their light was changing. Edwin Hubble used Cepheid variables observed with the Hooker telescope at Mount Wilson Observatory to show that some spiral nebulae were not small clouds inside the Milky Way. They were separate galaxies, lying far beyond our own. The universe suddenly became much larger than many had imagined. The Milky Way was not the whole cosmic city. It was one island of stars among many. Then Hubble, working with observations from Milton Humason and building on earlier redshift work by Slipher, helped establish the relationship now called the Hubble-Lemaitre law. In voiceover-friendly terms, the law says that more distant galaxies generally show greater redshift. The farther away a galaxy is, the more its light has been stretched. This does not mean every galaxy moves neatly away from us in a perfect pattern. Nearby galaxies can have their own local motions. The Andromeda Galaxy, for example, is moving toward the Milky Way because local gravity dominates between them. But on the larger scales, across immense cosmic distances, the pattern becomes clear. Space is expanding, and distant galaxies are carried farther apart as that expansion continues. The redshift of distant galaxies is not just a Doppler effect like the change in pitch of a passing siren, although that comparison can help a little. In cosmology, the light is stretched because space itself expands while the light travels. A photon crossing the universe is not moving through a perfectly fixed background. The background itself is changing, and the wavelength of the photon changes with it. This discovery transformed the Big Bang from a strange theoretical possibility into something increasingly connected to evidence. If the universe is expanding today, then the natural question is what it looked like yesterday, and the day before that, and billions of years before that. Follow the expansion backward, and galaxies were closer together. Matter was denser, radiation was hotter. The universe becomes less like the quiet star-filled darkness we see now, and more like an intensely hot early state. That is why the universe would not sit still. The equations of general relativity allowed motion on the grandest scale. Friedman and Lemaitre showed that an expanding universe made sense mathematically. Slipher, Leavitt, Hubble, and Humason helped supply the observational ladder that made expansion visible. Step by step, the cosmos changed from a static arena into a history. And once the universe has a history, the question of before becomes sharper. An expanding universe points backward toward a denser past. But whether that past reaches an absolute beginning, or only the earliest state our current physics can describe, remains the deeper mystery waiting behind the evidence. The strongest evidence for the hot Big Bang does not come from imagination. It comes from light. Not ordinary starlight shining from suns scattered through the night, but something older and quieter. A faint glow that fills the sky in every direction. It is not visible to human eyes, and it does not arrive as a bright flash or a beam from some single place. It is microwave radiation, stretched and cooled by the expansion of the universe, until it has become one of the coldest, softest signals in all of astronomy. This ancient light is called the cosmic microwave background. It is the oldest light we can directly observe from the early universe. In a very real sense, it is a photograph of the young cosmos, though not of the very first moment. It comes from roughly 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and for light to travel freely across space. Before that time, the universe was not empty and dark. It was hot, dense, and glowing, but it was also opaque. Space was filled with a plasma of charged particles, electrons, atomic nuclei, and radiation constantly interacting. Light could not simply travel in a straight line for long distances, because free electrons kept scattering it again and again. The young universe was more like a brilliant fog than a clear night sky. Then, as the universe expanded, it cooled. Eventually, electrons could join with atomic nuclei to form neutral atoms, mainly hydrogen and helium. Once those free electrons were no longer constantly in the way, light was able to travel through space without being scattered every few moments. The fog lifted. The universe became transparent. The radiation released at that time has been travelling ever since. Over billions of years, the expansion of space stretched that light into much longer wavelengths. What began as a hot glow in the early universe has cooled into microwave radiation, now only a few degrees above absolute zero. Its temperature today is about 2.7 degrees above absolute zero, which is astonishingly cold, only slightly warmer than the deepest possible physical cold. The existence of this radiation was not just guessed after it was found, it was predicted. In the 1940s, George Gamow, Ralph Alpher and Robert Herman worked on the consequences of a hot early universe. If the universe had once been extremely hot and dense, then the radiation from that early state should still exist. It should not have vanished. It should have been stretched, diluted, and cooled as the universe expanded, leaving behind a faint thermal afterglow. That was a remarkable idea. It meant the Big Bang model did not only explain expansion after the fact, it made a prediction. Somewhere in the sky, in every direction, there should be a cold, leftover glow from the early universe. Not a bright cosmic fireplace, sadly, which would have been more convenient for cold evenings, but a very faint signal hidden in the microwave part of the spectrum. Then, in 1965, Arno Penzias and Robert Wilson found it almost by accident. They were working at Bell Labs in New Jersey, using a large radio antenna known as the Holmdel horn antenna. They were trying to understand a persistent background noise in their equipment. It seemed to come from every direction. It did not disappear when they checked the instrument. It didn't match the usual sources of interference. They even cleaned out pigeon droppings from the antenna, which is one of the less glamorous but very real moments in the history of cosmology. Still, the signal remained. At the same time, nearby researchers at Princeton University, including Robert Dick, Jim Peebles, Peter Roll and David Wilkinson, had been preparing to search for the very radiation predicted by the hot Big Bang model. When the connection became clear, the strange noise detected by Penzias and Wilson was recognized as the cosmic microwave background. It was a turning point. The universe was not merely expanding, it carried an ancient thermal afterglow, exactly the sort of relic expected from a hot, dense beginning. One of the most important features of the cosmic microwave background is its remarkable smoothness. It arrives from every direction in the sky at almost the same temperature. This is exactly what the hot Big Bang model would lead us to expect from a universe that was once extremely hot, dense, and nearly uniform. It suggests that the early observable universe was not a chaotic mess of separate explosions, but a single connected state with very similar conditions across vast regions. That smoothness matters. If the Big Bang had been a normal explosion into empty space, there would be no obvious reason to expect such a uniform afterglow surrounding us from every direction. But if the entire observable universe was once filled with hot radiation and matter, then a nearly even glow across the sky makes far more sense. The cosmic microwave background is not perfectly smooth, and those tiny imperfections are also important. But its overall uniformity is one of the great pillars supporting the Big Bang model. Alongside cosmic expansion and the abundance of light elements, it gives the early universe a measurable physical reality. It is not just a story told backward from the present, it is a signal still arriving from the distant past. Yet this ancient light also reminds us of the limits of what we can see. The cosmic microwave background does not show the exact beginning. It does not show the first second. It does not reveal the moment when time itself may have behaved differently, or when gravity and quantum physics may have been tangled together in ways we do not yet understand. It shows the universe when it was already hundreds of thousands of years old. That is extremely early by cosmic standards, almost newborn compared with 13.8 billion years of history. But it is not the first instant. The universe had already passed through dramatic earlier stages before this light was released. So the cosmic microwave background gives us something precious and humbling at the same time. It is a powerful snapshot of the young universe, a quiet glow from a time before stars, before galaxies, before planets, and before anything like us could exist. It tells us that the hot Big Bang was real in the strongest observational sense. But when we ask whether there was a before, this oldest light can only take us so far. It brings us close to the beginning of the visible story, but not all the way to the edge of the page. The cosmic microwave background is often described as the afterglow of the early universe. But if it had been perfectly smooth, the story would have become rather awkward. A completely smooth universe is not a good recipe for stars. It is not a good recipe for galaxies, planets, chemistry, or small creatures, eventually wondering why the universe bothered being so complicated. If matter had been spread with absolute perfection in every direction, with no slightly denser regions and no slightly emptier regions, then gravity would have had very little to work with. Everything would have remained too even, too balanced, too featureless. Luckily for us, the early universe was not perfectly smooth. It was incredibly close to smooth, but not exactly. Hidden within the cosmic microwave background are tiny temperature variations, little differences from one patch of sky to another. These variations are extremely small, only around 1 part in 100,000. That means the early universe, at the time this light was released, was astonishingly uniform. But it was not blank. It had texture. It had the faintest beginning of structure. Those tiny differences mattered enormously. A slightly warmer or cooler patch in the cosmic microwave background points to tiny variations in density and motion in the early universe. Some regions contain just a little more matter and energy than nearby regions. Not much more, not enough to look dramatic at the time, but gravity is patient. It does not need the universe to begin with fully formed galaxies. It only needs a slight advantage, a small unevenness, a quiet place to start pulling. Over hundreds of millions of years, those slightly denser regions attracted more matter. Gas gathered. Dark matter formed invisible gravitational scaffolding. The first stars ignited. Galaxies began to grow. Galaxy clusters formed. Vast filaments and walls of matter slowly shaped the large-scale structure of the cosmos. The universe became less like a smooth glowing fog and more like a cosmic web. This is one of the most beautiful ideas in modern cosmology. The galaxies did not appear from nowhere. They grew from tiny ripples in the young universe. To study those ripples, scientists needed to measure the cosmic microwave background with extraordinary precision. One of the first major missions to do this was the Cosmic Background Explorer, often known by its spoken name, COBE. Launched by the National Aeronautics and Space Administration in 1989, COBE confirmed that the cosmic microwave background has an almost perfect thermal spectrum, just as expected from a hot early universe. It also detected tiny temperature variations across the sky. That discovery was a major moment. The cosmic microwave background had already shown that the early universe was hot and dense, but the tiny variations showed the seeds from which later structure could grow. It was like finding the faint pencil marks beneath an enormous painting. Later came the Wilkinson Microwave Anisotropy Probe, another mission from the National Aeronautics and Space Administration. It mapped the cosmic microwave background in greater detail, measuring the pattern of temperature variations across the sky. These measurements helped refine estimates of the universe's age, composition, geometry, and expansion history. Then the European Space Agency's Planck spacecraft produced an even more detailed map. Planck measured the cosmic microwave background with remarkable sensitivity, giving scientists one of the clearest views ever made of the infant universe. Not the universe at the very first instant, but the universe when it was around 380,000 years old, still young enough that its later galaxies were only faint possibilities written into tiny fluctuations. These missions did more than make impressive maps. They helped establish the standard modern picture of cosmology, known as the lambda cold dark matter model. The name sounds slightly like a password to a very exclusive physics cupboard, but the idea can be stated clearly. The lambda cold dark matter model describes a universe made from ordinary matter, dark energy, radiation, and expanding space. Ordinary matter is the stuff that makes atoms, stars, planets, dust, oceans, and people. Dark matter does not give off light, but it has gravity, and it helps explain how galaxies rotate, how galaxy clusters behave, how light bends around massive objects, and how structure grew in the early universe. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate on the larger scales. These ingredients are not added carelessly, just to make the numbers behave. Dark matter is supported by several independent lines of evidence, including the motion of stars inside galaxies, the motion of galaxies inside clusters, gravitational lensing, and the large-scale arrangement of galaxies across the universe. Dark energy is supported by observations of distant supernova, the cosmic microwave background, and measurements of large-scale structure that show the expansion of the universe is not merely continuing, but accelerating. In the lambda cold dark matter model, ordinary matter makes up only a small part of the total cosmic budget. Dark matter makes up a much larger share of the matter, and dark energy dominates the overall energy content of the universe today. This can feel strange because ordinary matter is the only part we directly touch and see. But cosmology has never promised that the universe would organize itself around human convenience. It has been fairly consistent about that. The tiny ripples in the cosmic microwave background fit beautifully into this model. They show how small early variations could grow into the enormous structures we observe now. They connect the young glowing universe to the later cosmic web. They let scientists compare theory with observation in detailed ways, testing whether the same model can explain early radiation, galaxy distribution, gravitational lensing, and cosmic expansion. And this brings us back to the question of before. The early universe leaves traces. Some of those traces are bright enough, or at least measurable enough for science to read them billions of years later. The cosmic microwave background is one of the most powerful of those traces. Its tiny ripples are not random decorative speckles. They are fossil evidence of the conditions that later shaped the cosmos. but the closer we try to move toward the beginning, the harder those traces become to read. The cosmic microwave background shows a very early universe, but not the first instant. The pattern of galaxies tells us how structure grew, but not necessarily what existed before the hot dense phase. The evidence is strong, but it is also layered, and the deepest layer remains partly hidden. So the universe gives us a remarkable clue. It was once smooth enough to reveal a common origin, but uneven enough to become interesting. From almost nothing in the pattern, everything visible began to gather, and in those tiny ripples, we see both the power of the Big Bang model and the quiet edge of the mystery beyond it. One of the quietest but strongest clues to the Big Bang is not found in the motion of galaxies or the glow of ancient light. It is found in the ingredients of matter itself. Look around the universe today, and it seems wonderfully complicated. There are rocky planets, icy moons, carbon-rich dust clouds, iron cores, oxygen in atmospheres, calcium in bones, gold in jewellery, and all the other elements that make reality feel pleasingly untidy. But the early universe did not begin with that full chemical cupboard already stocked. It began much more simply. In its first few minutes, the universe was hot and dense enough for nuclear reactions to happen almost everywhere. This early period is called Big Bang nucleosynthesis. The word nucleosynthesis simply means the making of atomic nuclei. It does not describe the making of full atoms with the electrons calmly arranged around them, because the universe was still far too hot for that. It describes the formation of the small nuclear cores that would later become the lightest elements. During this brief early window, the universe produced most of its hydrogen and helium, along with tiny amounts of lithium and related light nuclei. Hydrogen was mostly present as single protons. Helium formed when protons and neutrons fused together into helium nuclei. There were also small amounts of deuterium, a heavier form of hydrogen, and helium-3, another light isotope. But the grand result was simple. The universe emerged from its first few minutes dominated by hydrogen and helium. This happened because the early universe was changing very quickly. At first, it was too hot for stable atomic nuclei to survive. Protons and neutrons could form, but any fragile nuclei were easily broken apart by energetic radiation. As the universe expanded, it cooled. For a short time, the temperature became just right for nuclear fusion to build light nuclei. Then, as expansion continued, the universe became too cool and too spread out for those reactions to continue efficiently. It was a narrow cosmic opportunity. The universe did not sit politely at one temperature, waiting for chemistry to organize itself at leisure. It cooled rapidly, like a soup that had no interest in following the recipe. Nuclear reactions had only a few minutes to do their work. This is why the Big Bang did not make most of the heavier elements. Elements such as carbon, oxygen, silicon, iron, and gold require later environments. Carbon and oxygen are forged inside stars, where gravity squeezes gas to extreme pressures and temperatures over millions or billions of years. Iron is built in the lives and deaths of massive stars. Many of the heaviest elements, including much of the universe's gold, are produced in violent events such as supernova explosions and neutron star mergers, where nuclear reactions are driven under extraordinary conditions. So, in a very literal sense, the Big Bang made the simplest ingredients, and stars later did much of the complicated cooking. The early universe provided hydrogen and helium. Stars turned some of that material into heavier elements. Supernovae and neutron star mergers scattered those elements through space. Later generations of stars and planets formed from enriched gas. Eventually, somewhere in that long chain, chemistry became interesting enough to produce oceans, rocks, cells, and people wondering why gold could not have been made in a slightly more convenient way. The scientific study of these light elements became an important part of Big Bang cosmology. In the 1940s, Ralph Alpher, George Gamow, and Hans Bethe were connected with early work on the origin of elements in the hot early universe. Their famous paper became known as the Alpha-Beta-Gamma paper, partly because the names Alpha, Beth, and Gamma sounded like the first three letters of the Greek alphabet. It is one of the rare moments when physics allowed itself a small joke and somehow got away with it. The details of early nucleosynthesis have changed since those first ideas, because later research showed that the Big Bang could not create all the elements. Stars had to play the larger role in producing the heavier ones. But the central insight remained powerful. A hot early universe should leave behind predictable amounts of the lightest elements. This is where Big Bang nuclear synthesis becomes more than a nice story. It becomes a test. Nuclear physics tells scientists how protons and neutrons should have behaved in the early universe. It predicts how much hydrogen, helium, deuterium, and lithium should have formed, depending on the density, temperature, and expansion rate of the young cosmos. When astronomers measure the abundance of these light elements, especially in very old and chemically simple regions, the results broadly match the predictions of a hot early universe. In particular, the large amount of helium is extremely important. Roughly speaking, about 1/4 of ordinary matter by mass is helium, with most of the rest being hydrogen. Stars do make helium by fusing hydrogen, but not enough to explain the whole cosmic abundance. The universe appears to have started with a large supply of helium already present, exactly as Big Bang nucleosynthesis predicts. This gives science another independent pillar of evidence. Galaxy redshifts show that the universe is expanding. The cosmic microwave background shows that the early universe was hot, dense, and glowing. Big Bang nucleosynthesis shows that the early universe had the right conditions to forge the lightest nuclei in the right proportions. These are different kinds of evidence, coming from different parts of physics and astronomy, yet they point in the same direction. That agreement matters. A strong scientific model does not rest on one clue alone. It becomes more convincing when separate clues, measured in separate ways, fit together into the same larger picture. But this evidence also shows where the boundary lies. Big Bang nucleosynthesis tells us about the universe when it was a few minutes old. That is almost unimaginably early compared with the age of the cosmos today. Yet it is still not the absolute beginning. By the time light nuclei formed, the universe had already passed through earlier, hotter, stranger conditions. It had already expanded and cooled enough for protons and neutrons to exist in a useful way. It had already crossed stages that current physics can describe only with increasing difficulty. So the pattern continues. The farther forward we move from the earliest boundary, the stronger the evidence becomes. Once the universe reaches testable conditions, its history leaves measurable traces, elements, radiation, structure, motion. But the closer we move toward the first edge, the more difficult the evidence becomes to read. The hydrogen and helium spread across the cosmos are not just common materials. They are ancient witnesses. They tell us that the universe was once hot enough to build the first simple nuclei, but brief and cooling enough to leave the heavy work for stars. They do not answer every question about what came before, but they help confirm that whatever the deeper origin may have been, the universe we can observe passed through a real, measurable, fiery beginning. Before the universe became transparent, it was filled with light that could hardly go anywhere. That sounds strange at first because we often imagine light as the thing that lets us see across space. Light crosses rooms, oceans, planetary systems, and deep cosmic distances. It travels from stars to telescopes, from galaxies to detectors, and from a bedside lamp to the page of a book you are absolutely only going to read for 5 minutes. Light seems free by nature, but in the early universe, light was trapped in a glowing fog. Before atoms formed, the universe was a hot plasma. A plasma is a state of matter in which particles are not joined into neutral atoms, but exist as charged pieces moving freely. Instead of calm hydrogen atoms, with electrons bound around atomic nuclei, the young universe contained free electrons, free atomic nuclei, and radiation all mixed together in an extremely hot, dense sea. The key problem for light was the free electrons. Photons, the particles of light, kept running into these electrons. Every time a photon travelled a short distance, it was likely to be scattered again. It would strike an electron, change direction, and lose any simple path across the cosmos. The universe was glowing, but it was not clear. It was bright in the way a dense fog can be bright when headlights shine through it. There was light everywhere, but there was no long view. This is why the early universe was opaque. Opaque does not mean dark. It means light could not pass freely through it. The young universe was more like the inside of a glowing cloud than an open night sky. If an observer could somehow have existed there, which would have required some truly unreasonable heat resistance, they would not have seen distant galaxies or stars because those things did not yet exist. More importantly, they would not have seen very far at all. Light was constantly being scattered by the charged particles around it. As the universe expanded, it cooled. Expansion spread the energy out. The temperature dropped. Eventually, the universe became cool enough for electrons to join with atomic nuclei and form neutral atoms, mostly hydrogen and helium. This period is called recombination. The name can be a little misleading, because it sounds as though electrons and nuclei were combining again after having previously been together. In the early universe, however, this was really the first major formation of neutral atoms. The word recombination comes from the language of plasma physics, but in the cosmic story it marks the moment when the universe changed from an opaque plasma into a transparent cosmos. Once electrons were bound inside neutral atoms, they were no longer freely scattered everywhere. Photons could finally travel over enormous distances without being constantly interrupted. The glowing fog lifted. Space became clear. The light released at that time began its long journey through the expanding universe, eventually becoming the cosmic microwave background. That ancient light has been travelling for billions of years. As space expanded, its wavelength stretched. What began as a hotter glow in the young universe became cooler and softer. Until today it reaches us as microwave radiation, only a few degrees above absolute zero. It is not a light from the exact first instant, but it is the earliest light we can directly observe. To understand how the universe reached this point, it helps to trace the rough sequence of matter backwards. Today, ordinary matter is made from atoms. Atoms contain nuclei surrounded by electrons. Atomic nuclei are made from protons and neutrons. Protons and neutrons are made from quarks, held together by gluons through the strong nuclear force. But in the earliest conditions, the universe was so hot that even familiar protons and neutrons could not yet exist in the normal stable way. At extremely high temperatures, matter may have existed as a quark-gluon plasma. This is a state in which quarks and gluons are not locked inside individual protons and neutrons, but move through an intensely hot, dense medium. It is one of the strangest forms of matter that science can meaningfully discuss, and it gives physicists a way to think about conditions very close to the early universe. Experiments at the European Organisation for Nuclear Research in Geneva and at Brookhaven National Laboratory in the United States study matter under extreme conditions by colliding heavy atomic nuclei at very high energies. These experiments do not recreate the Big Bang as a whole, because the entire early universe cannot be squeezed into a laboratory, which is probably for the best from a health and safety perspective. But they can briefly create tiny droplets of matter hot enough to resemble the quark-gluon plasma that existed in the young cosmos. As the universe cooled, quarks became confined inside protons and neutrons. Then, during the first few minutes, some protons and neutrons fused into light atomic nuclei. Much later, when the universe was around 380,000 years old, electrons joined those nuclei to form neutral atoms. Only then could light travel freely enough to leave behind the cosmic microwave background. This sequence matters because it shows just how unfamiliar the early universe becomes as we move backward. The world we know is built from atoms. Atoms form molecules. Molecules form gases, rocks, oceans, cells. And the rather brave assumption that one more cup of tea will solve the evening. But before atoms, the universe was plasma. Before stable nuclei, it was a hotter mixture of particles. Before protons and neutrons, it may have passed through the quark-gluon plasma state. The farther back science goes, the less the universe resembles anything in ordinary experience. And that brings us back to the question of before. When people ask what happened before the Big Bang, the mind often imagines normal time filled with normal objects. Perhaps empty space, perhaps a previous universe, perhaps some kind of cosmic waiting room. But the early universe was not simply a familiar place with the temperature turned up. It was a state in which light could not travel freely, atoms could not exist, and matter itself behaved in ways that require particle physics to describe. So as we approach the beginning, the idea of an ordinary before becomes more fragile. Not meaningless necessarily, but fragile. The universe becomes less like a stage on which events happen, and more like a changing physical structure in which space, time, matter, and light are all part of the mystery. The first clear light we can see comes only after the fog lifted. Before that, science can still reason, calculate, and test pieces of the story. But the view becomes less direct, more difficult, and more dependent on the deepest laws of physics. The universe did not begin by looking like the universe. It had to become transparent. It had to cool into atoms. It had to allow light to cross the darkness. Only then could the cosmos begin to show us its face. The early universe was already strange enough before inflation enters the story. It was hot, dense, expanding, filled with radiation and particles, and moving toward the conditions that would eventually allow atoms, stars, galaxies, planets, and quiet questions in the middle of the night. But when scientists look closely at the universe we observe today, and especially at the cosmic microwave background, they found something that needed explaining. The young universe was not just hot and dense, it was astonishingly smooth. In every direction we look, the cosmic microwave background has almost the same temperature. There are tiny variations, and those variations are extremely important, but the overall sameness is remarkable. One patch of the ancient sky looks almost exactly like another patch on the opposite side of the observable universe. That might sound peaceful, and in a way it is. But for cosmologists, peace can be suspicious. The problem is that distant regions of the cosmic microwave background appear to be too far apart to have exchanged information with each other in the ordinary way. If light, heat, or any physical influence had not had enough time to travel between them, then how did they end up at almost the same temperature? How did the early universe become so evenly balanced across regions that should never have had time to coordinate their cosmic thermostat? This is called the horizon problem. The name comes from the idea that any region of the universe has a limit to how far signals could have travelled since the beginning. This limit is a kind of horizon. Without some extra explanation, different regions of the early universe should have been beyond each other's horizons. They should not have had time to settle into nearly matching conditions. And yet, when we observe the oldest light in the sky, the universe looks almost unbelievably even. Cosmic inflation was proposed as a way to solve this. Inflation is the idea that the very early universe underwent an extremely rapid expansion for a very brief period. This expansion was not just ordinary cosmic growth at a leisurely astronomical pace. It was a dramatic stretching of space itself, so fast and so early that a tiny region could have been blown up to enormous size. Alan Guth introduced one of the first major versions of inflationary theory in 1980. Other important figures, including Andrei Linde and Alexei Starobinsky, developed influential models and helped shape inflation into one of the central ideas in modern cosmology. Their work suggested that the smoothness of the observable universe might be explained if the regions we now see far apart were once close together, before inflation stretched them away from each other. In that picture, the early universe did have time to even out before inflation. Then inflation rapidly expanded that already smoothed region until it became far larger than the observable universe today. The result is a cosmos that looks nearly the same in every direction, not because distant regions somehow communicated across impossible distances, but because they were once neighbours before space stretched them apart. Inflation also helps with another puzzle, called the flatness problem. On the largest scales, the universe appears geometrically very close to flat. This does not mean flat like a sheet of paper floating in space. It means that the geometry of space, measured across enormous distances, is very close to the simple geometry where parallel lines remain parallel and the angles of large triangles behave in the familiar way. General relativity allows the universe as a whole to have different possible curvatures, depending on its contents and history. It could be positively curved, negatively curved, or extremely close to flat. The puzzle is that, without inflation, the early universe seems to have needed very finely balanced conditions to end up as flat as it appears today. Inflation offers a natural explanation. When space expands enormously, any original curvature is stretched out, rather like the surface of a balloon looking flatter and flatter if you could zoom in on a tiny patch as it grows. The whole balloon may still be curved, but the patch becomes so large and gently curved that it appears almost flat. Inflation does not only explain smoothness and flatness, it may also explain where the tiny ripples in the cosmic microwave background came from. According to quantum theory, even seemingly empty space is not perfectly still. Tiny quantum fluctuations can exist in fields. During inflation, these microscopic fluctuations could have been stretched to cosmic scales. What began as extremely small quantum variations may have become the seeds of later structure. Over time, gravity amplified them. Slightly denser regions pulled in more matter. Dark matter helped build the invisible scaffolding. Gas gathered, stars formed, galaxies assembled. Galaxy clusters and huge cosmic filaments took shape. In this way, inflation connects the smallest uncertainties of quantum physics to the largest structures in the universe. That is a beautiful idea, and also a mildly rude one, because it means the grand architecture of galaxies may have begun as tiny quantum wrinkles. The universe apparently has always had texture, still it is important to be careful. Inflation is a powerful and widely studied framework, and many of its broad predictions fit observations very well. The universe is smooth on large scales. It is close to flat. The pattern of tiny variations in the cosmic microwave background is broadly consistent with the kind of structure inflation can produce. But inflation is not completely settled in every detail. Scientists do not yet know the exact physical mechanism that drove it, if it happened in the simplest way. Many different inflationary models can produce similar observational results. The field or process responsible for inflation has not been directly identified. Evidence may strongly favour the general idea of a very early rapid expansion, but the precise story remains unfinished. This matters because inflation changes the meaning of the Big Bang. In older, simple descriptions, the Big Bang is treated as the earliest moment of the universe, but in many modern pictures, inflation may have occurred before the Hot Big Bang phase. The Hot Big Bang would then describe the universe after inflation ended, when energy was converted into the hot soup of particles and radiation that later cooled into the cosmos we observe. So inflation may describe something before the hot dense beginning usually called the Big Bang, but it may not be the final beginning of everything. It may push the question back rather than remove it. What caused inflation? Did inflation itself have a beginning? Was there a state before inflation? Could inflation be eternal in some direction? Or does the question become meaningless at a deeper boundary, where time itself is no longer familiar? Inflation gives science a remarkable bridge between the observed universe and its earliest known conditions. It explains why the cosmos looks smooth, why it seems close to flat, and why tiny early fluctuations could become galaxies. But it also opens another door. If the Big Bang was not simply the first instant, but the hot aftermath of an even earlier stretch, then the question of before becomes deeper, quieter, and stranger than ever. if we follow the expanding universe backward in time, the story becomes stranger with every step. Galaxies move closer together. The cosmic microwave background becomes hotter. Matter becomes denser. Atoms break apart into nuclei and electrons. Nuclei break into protons and neutrons. At still earlier stages, even those familiar particles belong to a world of extreme energies, quantum fields, and conditions far beyond anything in ordinary life. Keep rewinding this cosmic film using Albert Einstein's general theory of relativity, and the universe appears to move toward a boundary of enormous density and temperature. In the simplest classical picture, everything seems to be compressed into a state where distances shrink toward nothing. Density rises without limit, and the curvature of space-time becomes infinite. This is often called the Big Bang singularity. It is one of the most famous ideas in cosmology, but also one of the easiest to misunderstand. A singularity is sometimes imagined as a tiny physical dot containing the entire universe, sitting there in darkness until the Big Bang happened. That image is dramatic, but it can be misleading. The Big Bang singularity is not something astronomers have photographed. It is not an object floating somewhere. It is not a little cosmic seed hidden at a particular location in space. It is a boundary reached when the equations of general relativity are pushed backward as far as they can go. In physics, a singularity usually means that a theory has reached a point where it stops giving sensible answers. Quantities that should remain finite begin to become infinite. Density becomes infinite. Curvature becomes infinite. Temperature may be driven beyond meaningful description. These infinities are not always treated as literal features of nature. Very often, they are signs that the mathematical model is being stretched beyond the region where it can safely be trusted. That is not a failure in the ordinary sense. It is more like a map reaching the edge of the paper. The map may be accurate for every road, river, hill, and village it shows. But if you try to use it beyond the area it covers, the blank space does not mean the world definitely ends there. It means the map has stopped. General relativity is one of the greatest maps science has ever made. It describes gravity with astonishing precision across planets, stars, black holes, gravitational waves, and the large-scale universe. It tells us that matter and energy shape space-time, and that space-time guides the motion of matter and light. But near the earliest moments of the universe, gravity would have been extreme, density would have been immense, and quantum effects would almost certainly have mattered. This is where the trouble begins. General relativity is not a quantum theory. It describes space-time as smooth and continuous. Quantum physics, on the other hand, describes matter and fields in terms of probabilities, uncertainty, and discrete interactions. Both frameworks are incredibly successful in their own domains, which is useful, but also slightly inconsiderate, because the earliest universe seems to demand both at once. In the 1960s and 1970s, Roger Penrose and Stephen Hawking developed powerful mathematical results known as singularity theorems. Penrose first showed that, under certain conditions, general relativity predicts the formation of singularities inside black holes. Hawking then applied similar ideas to cosmology, showing that an expanding universe, when traced backward under certain assumptions, appears to lead to a singular beginning. These theorems were profound. They showed that singularities were not just awkward features of highly simplified models. They could arise quite generally from the structure of general relativity itself. If the universe obeyed certain conditions, then a pass boundary was not merely possible. It was extremely difficult to avoid. But the words "under certain conditions" matter. These singularity theorems rely on assumptions about gravity, energy, space-time, and causality. Those assumptions are reasonable within classical general relativity, but the earliest universe may not have been a purely classical place. If quantum gravity changes the behavior of space-time at extremely high densities, then the singularity predicted by classical relativity may be replaced by something else. It might be replaced by a bounce. It might be replaced by a quantum transition. It might be softened into a boundary where time behaves differently, or it might require a theory we have not yet properly found. The honest answer is that we do not know. This is why physicists are cautious with infinity. Infinity can be useful in mathematics, but in physical theories it often raises a warning flag. When a calculation says that a real object has infinite density or infinite temperature, scientists do not simply nod politely and accept that nature has handed them an actual infinite furnace. They ask whether the theory has been pushed beyond its valid range. A familiar example comes from older models of atoms. Classical physics could not fully explain why electrons did not spiral into atomic nuclei. The problem was not solved by accepting that atoms were impossible. It was solved by developing quantum mechanics, a deeper framework that changed the rules at small scales. In a similar way, the Big Bang singularity may be telling us that general relativity is missing something essential near the earliest boundary. That does not mean the Big Bang model collapses. The evidence for an early hot dense universe remains strong. Cosmic expansion, the cosmic microwave background, primordial light element abundances, and the growth of cosmic structure all point in the same direction. The singularity is not the whole Big Bang model. It is what appears when one particular theory, general relativity, is extrapolated backward to an extreme limit. So the singularity should be treated carefully. It is not a direct observation of the beginning. It is not a settled description of what physically existed. It is a signpost at the edge of known theory, pointing toward a place where gravity, quantum physics, space and time may need to be understood together. And this brings the question of before into sharper focus. If the Big Bang singularity were a literal beginning of time, then asking what came before might not make sense in the usual way. There would be no earlier moment for anything to occupy. But if the singularity is only a breakdown of current theory, then there may be a deeper description behind it. There may be a prior phase, a quantum origin, a bounce, an inflationary state, or some structure that does not fit neatly into ordinary before and after. The singularity, then, is not an answer so much as a boundary. It tells us that the road of well-tested physics leads back to a remarkable edge. Beyond that edge, our current map becomes uncertain. The universe may not be saying, "This is where everything began." It may be saying, "This is where your present theory can no longer follow me." Time feels like the most reliable thing in the world, until physics begins gently interfering. In ordinary life, time seems to flow everywhere in the same steady way. A second is a second. A minute is a minute. The clock on the wall, the watch on your wrist, the phone beside your bed, and the slightly accusatory kitchen timer all seem to belong to one shared rhythm. Time appears to be a universal background, quietly ticking behind everything else. But modern physics does not see time quite like that. Albert Einstein's special theory of relativity, introduced in 1905, showed that time is not absolute in the simple everyday sense. It does not pass identically for all observers in all circumstances. Instead, measurements of time depend on motion. Two observers moving differently can disagree about how much time has passed between events, and both can be correct within their own frame of reference. This is not because one clock is broken, or because someone has been careless with the batteries. It is because space and time themselves are woven into the rules of nature. The speed of light in a vacuum is the same for all observers, and that single fact forces measurements of time and distance to adjust depending on relative motion. One of the most important consequences is time dilation. A moving clock can tick more slowly relative to an observer who's not moving with it. This effect is usually tiny at everyday speeds, which is why walking to the kettle does not turn you into a time traveller in any useful sense. But at speeds close to the speed of light, the effect becomes dramatic. Time is not a separate universal river carrying everything along at the same rate. It is part of the physical relationship between observers, motion, and light. Then Einstein's general theory of relativity made the picture even deeper. General relativity, completed in 1915, describes gravity as the curvature of space-time. matter and energy shape space-time, and that curved space-time guides the motion of matter and light. In this theory, time is also affected by gravity. A clock deeper in a gravitational field ticks more slowly than a clock farther away from that gravitational influence. This is called gravitational time dilation. Near Earth, the effect is small, but it is real. A clock at sea level ticks very slightly differently from a clock high above Earth's surface. A clock on a satellite ticks differently from a clock on the ground, partly because of its speed and partly because it is in a weaker gravitational field. These differences are not philosophical decorations, they are measured effects. Satellite navigation systems have to account for relativity. The clocks on satellites and the clocks on Earth do not tick at exactly the same rates. If engineers ignored the effects predicted by special relativity and general relativity, position calculations would quickly become inaccurate. So the idea that time changes with motion and gravity is not only tested in laboratories, it quietly helps people find airports, restaurants, and occasionally their own house after taking a wrong turn with complete confidence. This is the important point. Time is physical. It is not just an invisible stage on which the universe performs, it is connected to motion, gravity, energy, and the structure of space-time itself. And that makes the question of what happened before the Big Bang much more delicate than it first appears. A key figure in this shift was Hermann Minkowski, who had once taught Einstein mathematics. In 1908, Minkowski introduced a powerful way of understanding special relativity. He described space and time as parts of a single combined structure, space-time. In this view, events are not located only somewhere in space. They are located somewhere in space-time, with both spatial position and time woven into the description. This does not mean space and time are identical in every way. Time still has a different character from the three dimensions of space. You can move left, right, forward, backward, up, or down in space, at least within the ordinary limits of furniture and walls. But you cannot stroll into yesterday in quite the same casual manner. Still, relativity showed that space and time are not completely separate ingredients. They mix together depending on motion and gravity. Cosmology often uses a concept called cosmic time. This is a useful way of describing the age and evolution of the universe on the larger scales. In the standard cosmological picture, scientists can define a kind of average time measured by observers who move along with the overall expansion of the universe. This allows cosmologists to say that the universe is about 13.8 billion years old, or that the cosmic microwave background was released about 380,000 years after the hot Big Bang. Cosmic time is extremely useful. Without it, telling the history of the universe would become unnecessarily awkward, and cosmology already has quite enough awkwardness to be getting on with. But cosmic time is not the same as the old idea of one absolute universal clock ticking independently of everything else. It depends on the large-scale structure and expansion of the universe. It is a natural time coordinate within a particular cosmological model, not a separate object existing outside reality. And this is where the title becomes truly interesting. If time was simply an eternal container, then asking what happened before the universe might seem straightforward. You would imagine time stretching backward forever, with the universe appearing at some moment within it. There would be an empty earlier period, then the Big Bang, then everything after. But if time is part of the universe's physical structure, the question changes. If the Big Bang, or some earlier boundary close to it, involved the origin or transformation of space-time itself, then before the universe may not refer to an ordinary earlier time. It may be like asking what is north of the North Pole. That analogy is often used because it captures something subtle. On Earth, north is a meaningful direction across most of the planet. You can travel north from London, north from Cairo, north from almost anywhere. But when you reach the North Pole, the direction stops working in the usual way. Asking what lies north of it does not reveal a hidden extra patch of Earth. It shows that the coordinate system has reached a boundary. The analogy does not prove there was no before the Big Bang. It should not be used too strongly. The universe is not literally a globe with time painted on it, and cosmology is not solved by a geography metaphor, however politely delivered. But it helps explain why ordinary language may fail near the deepest boundary of cosmic history. There may have been a prior phase. There may have been a bounce, an inflationary state, a quantum origin, or some deeper description in which time behaves differently. Or it may be that time, as we understand it, does not extend beyond that boundary at all. The central lesson is that time is not a simple universal clock standing outside the universe. It is one of the things physics must explain, and if time itself belongs to the structure of the cosmos, then the question of before is not just asking for an earlier event. It is asking whether earlier still means anything when the clock is part of the mystery. There is a point in the early universe where even our best tested theories begin to lose their footing. Not because scientists have become careless, or because cosmology suddenly gives up and has a little lie down, although that would be understandable. It happens because the universe, when traced back far enough, enters conditions so extreme that the rules we use so confidently today may no longer be complete. This earliest known boundary is often discussed in connection with the Planck era. The Planck era refers to an unimaginably early regime in cosmic history, so close to the beginning that our current understanding becomes uncertain. It is usually associated with times earlier than the Planck time, a tiny interval far less than a trillionth of a trillionth of a trillionth of a second. That phrase still does not really capture how small it is. Human language is not especially comfortable at that scale. It starts making a noise like a cupboard full of spoons. The name comes from Max Planck, the German physicist whose work helped open the door to quantum theory. Planck studied the problem of black body radiation, the light emitted by objects depending on their temperature, and his work led to the idea that energy could come in discrete amounts. This was one of the first cracks in classical physics, and it eventually helped lead to the quantum revolution. Planck's name is also attached to a set of natural units built from fundamental constants of nature. These include the speed of light, the gravitational constant, and Planck's constant, which is central to quantum physics. When these ingredients are combined, they define scales of length, time, mass, and energy, where gravity and quantum effects are expected to become deeply entangled. That is why the Planck era is so important. To describe most of the large-scale universe, scientists use general relativity. Albert Einstein's general theory of relativity describes gravity as the curvature of space-time. It works spectacularly well for planets, stars, galaxies, black holes, gravitational waves, and the expansion of the universe. It is one of the strongest scientific theories ever made. To describe the smallest ingredients of matter and the forces between them, scientists use quantum field theory. This framework treats particles as excitations of underlying quantum fields. It is the language behind the standard model of particle physics, which describes particles such as electrons, quarks, photons, gluons, and the Higgs boson. Quantum field theory has been tested with extraordinary precision in laboratories and particle accelerators. The difficulty is that general relativity and quantum field theory do not yet combine into one complete, tested theory of quantum gravity. Most of the time, this is not a disaster. If scientists are studying a planet orbiting a star, they can usually use general relativity or even Newton's older theory of gravity, depending on the precision needed. If they are studying particle interactions inside an accelerator, they can use quantum field theory, while mostly ignoring gravity, because gravity is incredibly weak compared with the other forces at particle scales. But the earliest universe does not allow that comfortable separation. Near the Planck era, the universe would have been enormously dense, enormously hot, and incredibly small in scale. Gravity would have been extreme, but quantum effects would also have been unavoidable. It is precisely the kind of situation where general relativity and quantum theory both seem necessary at once. And that is the wall. Not a physical wall floating in space, of course. There was no brickwork at the beginning of time, which is probably for the best. It is a wall of understanding, a boundary where our best tested theories tell us that something deeper is needed, but where the deeper theory has not yet been confirmed. Several candidate approaches have been developed. String theory proposes that the most fundamental ingredients of reality may not be point-like particles, but tiny vibrating strings with different vibrations corresponding to different particles. It also naturally includes a quantum description of gravity, at least in its mathematical structure. Loop quantum gravity takes a different route, attempting to quantize space-time itself, suggesting that geometry may have a discrete structure at the smallest scales. Both approaches are serious attempts to understand quantum gravity. Both have inspired important mathematics and physics. But neither has yet been confirmed as the final description of the universe's earlier state. They remain possible routes, not settled destinations. This is why the Planck era should be handled carefully. It is not unknown simply because nobody has looked hard enough with a better telescope. The conditions involved are far beyond direct experimental access. We cannot build a machine that recreates the entire first instant of the universe. We cannot place a detector outside the Big Bang and take notes with a clipboard. The universe is inconvenient in that way. Scientists can still make progress. They can study particle physics, black holes, gravitational waves, cosmic microwave background patterns, early universe models and mathematical theories of quantum gravity. They can search for clues left behind by extremely early processes. But the Planck era itself remains hidden behind a deep physical limit. This matters for the question of whether there was a before. If we ask what happened before the Big Bang, we're often asking about a region of reality that may lie beyond the reach of ordinary tested physics. The hot Big Bang model is strongly supported after the universe reaches conditions we can describe and compare with evidence. Expansion, light element formation, the cosmic microwave background, and galaxy structure all give science a firm path through cosmic history. But closer to the beginning, that path becomes less certain. The Planck era is where the question may stop being a simple historical inquiry and become a question about the foundations of physical law. Did time begin there? Did space-time emerge from something deeper? Was there a prior state, a bounce, a quantum transition, or no ordinary before at all? At the moment, science does not have a final answer. The Planck era is not a blank space where anything goes. It is a disciplined mystery, shaped by what is already known and constrained by what future theories must explain. It is the place where the map of tested physics reaches its most delicate edge, and somewhere near that edge, the question of before waits quietly, not yet solved, but not forgotten. One possible answer to the question of before is not that something ordinary happened earlier, but that earlier itself may stop behaving like an ordinary idea. That is difficult to picture, because our minds are built from experience inside time. We remember yesterday. We notice today passing. We expect tomorrow. Events seem to line up in a familiar order, like beads on a string. First this happened, then that happened, then someone put the kettle on and briefly restored civilization. So when we ask what happened before the Big Bang, it feels natural to imagine another bead on the string. The universe begins here, so perhaps there must be something just before it. A previous moment, a hidden cause, a dark empty stage waiting for the cosmic story to begin. But some scientific models suggest that this picture may not be the right one near the earliest boundary of the universe. One of the most famous attempts to describe such a possibility is the Hartle-Hawking no-boundary proposal, developed by the physicists James Hartle and Stephen Hawking. It is a proposal in quantum cosmology, meaning it tries to apply quantum ideas to the universe as a whole. Its aim is not simply to describe the universe after the hot Big Bang, but to ask whether the universe could have a beginning without a sharp edge in ordinary time. The phrase no boundary does not mean no universe. It does not mean no beginning in any possible sense. It means that the earliest state of the universe may not be a hard starting point where time suddenly switches on like a lamp. Instead, near the deepest boundary, time may behave in a way that is closer to a spatial dimension. That sentence is simple to say and very difficult to imagine, which is a polite way of saying that the universe is once again refusing to be convenient. In ordinary life, time feels different from space. You can move through space in different directions. You can walk across a room, turn around, come back, and pretend you entered the room for a reason. Time does not behave that way. We experience it as having a direction. We move from past to future, not from Tuesday to last Wednesday by taking a brisk left turn. But in the Hartle-Hawking proposal, the earliest region of the universe is described using a mathematical transformation in which time loses some of its ordinary time-like character. Near the beginning, the distinction between time and space becomes less familiar. The universe can be finite, but without a sharp temporal edge. A common comparison is the surface of Earth. If you travel north, you can keep going until you reach the North Pole. But the North Pole is not an edge where Earth's surface suddenly breaks off. It is not a cliff with a little sign saying, "Please mind the end of geography." It is a point where the direction north stops working in the usual way. You cannot go farther north, not because there is a wall, but because the coordinate has reached a place where the question no longer applies as it did before. The no-boundary proposal uses a somewhat similar idea for the beginning of the universe. The universe may have an earliest region, but not a boundary before which ordinary time continues. Asking what happened before may be like asking what lies north of the North Pole. The words are understandable, but the direction has stopped behaving normally. This is only an analogy. The universe is not literally the surface of Earth. Time is not simply latitude. The beginning of the cosmos is not located somewhere in the Arctic, which is probably disappointing to anyone hoping for a very unusual expedition. But the comparison helps with the central idea. Something can be finite without having an edge in the ordinary sense. The no-boundary proposal is mathematically motivated, not visually obvious. It does not make the beginning of the universe easy to picture. It does not give us a simple little scene before the Big Bang, with space waiting patiently and time checking its watch. It asks us to imagine that the rules of time themselves may change near the deepest origin. It is also not proven. This is important. The Hartle-Hawking, no-boundary proposal is a serious scientific idea, but it is not a confirmed final answer. It belongs to the difficult borderland where general relativity, quantum theory, and cosmology all meet. Scientists can explore its mathematics, compare its implications with possible observations, and debate whether it gives a convincing account of the earliest universe. But it has not been established in the same way as the expansion of the universe, the cosmic microwave background, or the abundance of light elements. Its value is not that it closes the mystery. Its value is that it shows one way the mystery might change shape. Instead of asking what happened before the Big Bang, the no-boundary idea asks whether before applies at all near the boundary. If ordinary time is part of the universe's structure, then the origin of the universe may not be an event sitting inside a larger time. It may be a limit of time itself, or a region where time becomes something less like the ticking clock we know. This also helps clarify a common phrase, creation from nothing. In popular language, nothing usually means absolute nothingness. No space, no time, no matter, no energy, no laws, no fields, no hidden stage, no quiet cupboard where the universe was waiting to be assembled. Philosophers and theologians have discussed that kind of nothing for centuries, but in scientific cosmology, words like nothing can mean something more technical. They may refer to the absence of classical space-time, or to a quantum state that is not ordinary empty space, or to a mathematical boundary condition. This is not the same as everyday nothing, and it is not necessarily the same as philosophical nothingness. It is very important not to quietly swap one meaning for another and hope nobody notices. The no-boundary proposal does not say, in a simple everyday sense, that the universe came from blank emptiness. It suggests a possible way for the universe to be described without needing a prior moment in ordinary time. That is subtler, stranger, and more scientifically careful. And this brings the question back into focus. Some models do not answer what came before the Big Bang by placing another event before it. They suggest that the question may dissolve near the origin, because the word before depends on time, and time may not extend past that boundary in the familiar way. If that is true, then the Big Bang was not preceded by an empty room, a waiting clock, or a silent countdown. The earliest universe may have been more like a rounded edge of reality, finite yet without a previous moment in the ordinary sense. It is not the only possibility. It may not be the correct one. But it reminds us that the deepest questions are sometimes not answered by filling in a missing scene. Sometimes they are answered by discovering that the scene, the clock, and the word before all belong to the universe we were trying to explain. Another way to think about the beginning is not as a smooth rounded boundary, but as a kind of quantum transition. This idea is associated with the physicist Alexander Vilenkin, who developed a tunneling proposal for the origin of the universe. It is one of the bold attempts in quantum cosmology to describe how a universe might emerge from a quantum state, without beginning as a classical object sitting inside a larger space and waiting for time to start ticking. To understand the idea gently, it helps to begin with quantum tunneling itself. In ordinary classical physics, some barriers cannot be crossed unless an object has enough energy. A ball rolling up a hill, for example, will not reach the other side if it lacks the energy to get over the top. It rolls part way up, slows down, stops, and rolls back. Classical physics is very firm about this. Not enough energy means no crossing. The hill is not interested in your optimism. Quantum physics is stranger. For a quantum system, such as an electron, the rules are not described by a simple little object following one definite path like a tiny marble. Quantum systems are described by probabilities. Their behavior is connected to a wave function, which gives a mathematical description of the possible outcomes that may be found when the system is measured. Because of this wave-like behavior, there can be a non-zero probability that a particle appears on the other side of a barrier that classical physics would say it could not cross. This is quantum tunneling. It does not mean the particle digs a tunnel in the ordinary sense. There is no tiny shovel, no hard hat, and no deeply committed electron construction crew. It means the quantum description allows a transition through a classically forbidden region. This is a real effect. Quantum tunneling helps explain radioactive decay, nuclear fusion in stars, tunnel diodes, scanning tunneling microscopes, and many other phenomena in physics and technology. But applying tunneling to the entire universe is a much more difficult and speculative idea. When scientists observe quantum tunneling in a laboratory, they're usually studying particles or systems within an already existing spacetime. There is a laboratory, an apparatus, a clock, a surrounding environment, and a larger universe in which the tunneling event takes place. The experiment is unusual, but the setting is familiar enough. Vilenkin's tunneling proposal is far more ambitious. It tries to apply a quantum idea not to one particle inside the universe, but to the universe as a whole. In this picture, the universe may emerge through a quantum tunneling process from a state described, in technical language, as nothing. That word needs very careful handling. In everyday speech, nothing usually means an empty room, a dark space, a blank patch, or the absence of familiar things. But ordinary empty space is still something. It has dimensions. It can contain quantum fields. It has physical laws. It has structure. It is not absolute nothingness in the deepest philosophical sense. In quantum cosmology, when a proposal speaks of a universe tunneling from nothing, it does not usually mean a universe popping out of ordinary empty space. Nor does it simply mean magic with equations standing nearby looking respectable. It means an attempt to describe the universe emerging from a state with no classical space-time, no ordinary space, no ordinary time, and no pre-existing stage in which the event happens. That is why the idea is so strange. A universe from quantum tunneling is not like a spark appearing in a dark room. There is no room, there is no clock on the wall, there is no outside place from which to watch. The model is trying to describe the origin of the room, the clock, the wall, and the physical meaning of watching in the first place. Vilenkin's proposal differs from the Hartley-Hawking no-boundary proposal, though both are attempts to avoid the simple classical singularity. The Hartley-Hawking no-boundary idea imagines the earliest universe as finite, but without a sharp edge in ordinary time, with time behaving more like a spatial dimension near the boundary. In that picture, the question of before may dissolve because the direction of time stops applying in the usual way. Vilenkin's tunnelling approach keeps a different flavour. It describes the universe as emerging through a quantum transition from no classical space-time into an expanding state. Instead of smoothing away the beginning into a rounded no-boundary geometry, it treats the beginning more like a tunnelling event into existence. Although even that phrase must be used cautiously, because existence itself is what the model is trying to describe. Both ideas are serious scientific proposals. Both use the language of quantum cosmology. Both try to deal with the problem that classical general relativity, when followed backward, appears to run into a singularity. And both suggest that the earliest universe may not be understood by simply imagining an earliest normal moment. But neither has been proven. This is the calm but important limitation. The beginning of the universe is not accessible in the same way as an electron tunnelling through a barrier in a laboratory. We cannot repeat the creation of the universe many times and take careful notes, which is probably fortunate for everyone's scheduling. We cannot place measuring devices outside space-time. We cannot directly observe the transition from no classical space-time into the early universe. Scientists can study the mathematics. They can ask whether a proposal is internally consistent. They can compare its possible consequences with observations of cosmic structure, inflation, and the cosmic microwave background. They can explore whether it fits with a broader theory of quantum gravity, but the evidence is not yet decisive. So what does this mean for the question of before? It shows that some models allow an origin without a normal before. In Vilenkin's tunnelling proposal, the universe is not necessarily preceded by an ordinary earlier universe ticking along in time. It may emerge from a quantum state where ordinary space and ordinary time are not yet present. In that case, before is not a hidden scene waiting just off stage. It is a word that may not have found its stage yet. Other models leave room for deeper prior conditions. Inflationary theories, bouncing cosmologies, cyclic models, and other approaches may suggest something before the hot Big Bang phase. But tunnelling proposals remind us that the deepest origin might not be a previous event in time. It might be a transition into time. That is what makes the question so delicate. The Big Bang may not be the final beginning, but it may also not have a before in the ordinary sense. Somewhere near the first edge of the cosmos, the difference between something earlier and time itself becoming meaningful may be the very mystery we are trying to understand. Inflation already makes the early universe feel strange. Eternal inflation makes it stranger still. In the simplest version of inflation, the very early universe undergoes a brief, incredibly rapid expansion. Space stretches enormously. Tiny quantum fluctuations are enlarged into the seeds of galaxies, and then inflation ends. The energy driving that expansion is converted into a hot, dense sea of particles and radiation. This is the beginning of the hot Big Bang phase, the part of the story that later leads to atoms, stars, galaxies, planets, and eventually someone lying awake wondering whether reality may have overdone the complexity slightly. But in some versions of inflation, the process does not end everywhere at once. Instead, inflation may stop in some regions while continuing in others. A region where inflation ends can become a hot Big Bang universe, filled with particles, radiation, and expanding space. Meanwhile, beyond that region, inflation may carry on, stretching space at an extraordinary rate. Other regions may later stop inflating too, each one beginning its own hot Big Bang phase. This idea is called eternal inflation. The word eternal should be handled carefully. It does not automatically mean eternal in every possible direction of time, or that the whole system has no beginning at all. It means that, in some models, inflation can continue indefinitely into the future in at least some regions, even while it ends locally in others. The result is a universe, or perhaps a larger cosmic structure, in which many separate regions like ours could form. Andre Linde is one of the major figures connected with eternal inflation and chaotic inflation. His work helped develop the idea that inflation might not be a single neat event that happened once everywhere, but a process capable of producing many expanding regions. In this picture, what we call the observable universe may be only one region where inflation ended and the hot Big Bang began. This is where the multiverse question appears. The multiverse, in this context, is not a proven collection of parallel worlds where every possible version of you has chosen a different biscuit. It is a theoretical possibility arising from certain models of inflation. If inflation continues in some places while ending in others, then our observable universe could be one bubble or one region within a much larger inflating background. Other regions might exist far beyond anything we can observe, separated from us by expanding space and by the limits of light travel. This does not mean the multiverse has been observed. It has not. That distinction matters. Eternal inflation is a serious idea in theoretical cosmology, but the possible regions beyond our observable universe may be permanently out of reach. If light or any signal from those regions can never arrive here, then direct testing becomes extremely difficult. Science works best when ideas can be connected to observation, measurement, and prediction. A model that produces unobservable regions is not automatically wrong, but it becomes harder to confirm in the usual way. Still, eternal inflation changes the meaning of the question. What came before the Big Bang? If our hot Big Bang was the local end of inflation in our region, then there may have been an inflating state before it. The Big Bang would still be real. The universe would still have passed through a hot, dense early phase. The cosmic microwave background, the abundance of light elements, and the growth of galaxies would still remain central evidence. But the Big Bang would not necessarily be the absolute beginning of everything. It would be the beginning of our local hot expanding region. That is a subtle but important shift. It is like discovering that the first page of a book may not be the first page of the entire library. It is still the first page of the story we can read. It still matters, but it may not be the first page of all possible writing. Eternal inflation also brings a serious scientific difficulty known as the measure problem. In simple terms, if inflation produces vast numbers of regions, perhaps even infinitely many in some mathematical descriptions, then it becomes hard to say what is likely or unlikely. Probabilities need a way of counting possibilities. But how do you count regions in a universe where inflation may keep producing more and more of them? How do you compare one kind of region with another if the total number may be endless, or if different ways of counting give different answers? This is the measure problem. It is not just a technical nuisance hiding in the corner. It affects how scientists make predictions in eternal inflation. A theory should not merely say that all sorts of things happen somewhere. It should help explain why we observe this universe, with these properties, rather than some wildly different one. If every possible outcome happens in some region, then the challenge becomes working out which outcomes should be expected and how those expectations can be tested. That is one reason eternal inflation remains both fascinating and controversial. It offers a powerful way to think about what may have preceded our hot Big Bang phase. It naturally grows out of some inflationary models. It may help explain why our observable universe appears smooth, flat, and seeded with tiny fluctuations. But it also raises difficult questions about observation, prediction, and whether regions beyond our cosmic horizon can ever be part of testable science. So eternal inflation does not give a simple answer. It gives a possible picture. In that picture, the Big Bang was not necessarily the birth of all reality. It may have been the moment inflation ended here, in the region that became our observable universe. Before our hot Big Bang, there may have been an inflating background. Beyond what we can see, there may be other regions where inflation ended differently, perhaps with different histories or even different physical conditions. Or this may not be the correct picture at all. The important point is that the Big Bang can be real without being the absolute beginning. Our universe can have a hot, dense early state, strongly supported by evidence, while the deeper origin remains unresolved. Eternal inflation is one path through that mystery. It does not close the question of before, it opens it wider, into a cosmic landscape where our beginning may have been local, not final. One of the clearest ways the Big Bang could have a before is if the universe did not begin by appearing from nothing, but by changing direction. This is the central idea behind bouncing cosmology. In a bouncing model, the hot expanding universe we observe today may have been preceded by a contracting phase. Instead of cosmic history starting at an absolute beginning, the universe may have existed in some earlier state, shrinking rather than expanding. That contraction could have continued until matter, energy, space, and gravity reached an extreme condition. Then, instead of collapsing into a final singularity, the universe may have passed through a transition and begun expanding again. In simple terms, the universe contracts, reaches a very dense state, and then bounces. That image is easy to say, but the physics behind it is not simple. A bounce is not like a rubber ball hitting the floor, or a balloon being squeezed and then released. There is no outside floor, no cosmic hand, and no larger room in which the universe performs its little rebound. The bounce would be a change in the behavior of spacetime itself. The scale of the universe would stop decreasing and begin increasing. A contracting cosmos would become an expanding one. This idea is appealing because it gives the phrase before the Big Bang a more literal meaning. Before the hot expanding phase, there may have been an earlier contracting phase. Time would not necessarily stop at the boundary. The Big Bang would not be the absolute first moment of reality, but the beginning of expansion after a previous cosmic collapse. Bouncing cosmology also tries to deal with the problem of the classical singularity. In ordinary general relativity, if the expanding universe is followed backward far enough, the equations seem to point toward a state of infinite density and infinite curvature. But many physicists suspect that this singularity is not a real physical object. It may be a sign that general relativity is being pushed beyond its proper range. A bounce offers one possible replacement. Instead of a singular beginning, new physics may create a transition from contraction to expansion. That new physics might involve quantum gravity, exotic forms of energy, extra dimensions or modifications to the behavior of gravity under extreme conditions. Different bouncing models use different mechanisms, and this is one reason the subject remains unsettled. The broad idea is simple, the details are difficult. Paul Steinhardt and Neil Turok are two major scientists associated with ekpyrotic and cyclic models of the universe. The word ekpyrotic comes from an ancient Greek idea of cosmic renewal through fire, though the modern scientific model is much more mathematical than mythological. In these models, the hot Big Bang phase may have been produced by a collision or interaction involving higher dimensional structures, often described in the language of brains from string theory. In cyclic versions, the universe may pass through repeated phases. Expansion may be followed by a long evolution, then some form of contraction or renewal, then another hot beginning. The Big Bang becomes not the single origin of everything, but one phase in a larger cosmic cycle. These ideas are serious theoretical alternatives, but they are not established replacements for the standard cosmological model. The standard picture, built around the hot Big Bang, cosmic expansion, the cosmic microwave background, primordial nucleosynthesis, dark matter, dark energy, and often inflation, remains the dominant framework because it fits a wide range of observations. Bouncing models must do at least as well. They must explain the smoothness of the early universe, the tiny fluctuations that became galaxies, the abundance of light elements, the cosmic microwave background, and the large-scale structure we observe today. That is a demanding task. The scientific appeal of a bounce is easy to understand. It removes the need for a hard beginning where physics simply breaks down. It allows time to extend before the hot Big Bang phase. It offers a possible answer to the question that has been quietly following us all along. Yes, perhaps there was a before, and perhaps that before was a universe contracting toward an extreme state. But appeal is not proof. A successful bouncing model must make predictions that can be compared with observations. It cannot simply be an elegant story. It needs to produce the right pattern of density variations, the right cosmic microwave background structure, and the right later universe. It must also avoid problems that can arise during contraction, such as growing irregularities or instabilities that could make the universe too messy to bounce into the smooth cosmos we observe. This is where bouncing cosmology differs sharply from inflation. Inflation explains the smoothness and flatness of the observable universe by proposing a very early period of extremely rapid expansion. Tiny quantum fluctuations are stretched to cosmic scales and later become the seeds of galaxies. The universe becomes smooth because a small region is expanded enormously. Bouncing models try to explain similar features with a very different story. They suggest that a previous contracting phase may smooth, shape, or prepare the universe before the bounce. Instead of a tiny region inflating into the cosmos we see, the universe passes through a transition from contraction into expansion, carrying certain patterns across that boundary. Both ideas are attempts to explain why the early universe had the conditions it did. Both are trying to look behind the hot Big Bang phase, but they imagine very different histories. Inflation says the hot Big Bang may have followed a strange early stretch. Bouncing cosmology says it may have followed an earlier collapse. Neither possibility should be treated casually as settled fact. But the bounce is one of the clearest scientific routes by which before the Big Bang could mean something ordinary enough to recognize. An earlier period of cosmic time, with events, change, and physical evolution. If a bounce is correct, then the Big Bang was not the first note. It was the turning point. It was the moment the universe stopped falling inward and began opening outward. And somewhere on the far side of that transition, hidden behind conditions we do not yet fully understand, there may have been a previous cosmic story whose traces are faint, difficult, and not yet securely read. One possible way to avoid the Big Bang singularity comes from an attempt to take the quantum nature of spacetime seriously. This idea belongs to loop quantum cosmology, a simplified cosmological application of a broader approach known as loop quantum gravity. The basic aim of loop quantum gravity is to understand gravity in quantum terms. Instead of treating spacetime as a perfectly smooth background that can be divided forever into smaller and smaller pieces, it asks whether spacetime itself may have a kind of quantum structure at the smallest scales. That is already a very strange idea. We're used to thinking of quantum physics as something that happens inside space. Electrons behave quantum mechanically. Photons behave quantum mechanically. Atoms, fields, and particles follow rules that do not always match everyday intuition. But space and time themselves are usually imagined as the stage on which those things happen. Loop quantum gravity suggests that the stage may also have quantum properties. Abhay Ashtekar is one of the central figures in the development of loop quantum gravity. His work helped reformulate general relativity in a way that made it possible to apply quantum methods to geometry itself. Martin Bojewald is one of the important figures associated with loop quantum cosmology, especially in exploring how these ideas might change the earliest universe. The central idea can be put gently. In general relativity, spacetime is smooth. Matter and energy curve it, and that curvature is what we experience as gravity. But if spacetime has quantum properties at extremely small scales, then its behavior at enormous densities may not be the same as the behavior predicted by classical general relativity. That difference becomes crucial near the Big Bang. In the classical picture, if we follow the expanding universe backward, the density keeps rising, and the curvature of space-time keeps increasing. Eventually, the equations point toward a singularity, a place where density and curvature appear to become infinite. But if space-time is quantum, then this smooth, classical picture may break down before infinity is reached. In loop quantum cosmology, the universe can behave differently at very high density. The quantum structure of geometry can modify the equations that describe expansion and contraction. Instead of collapsing all the way into a singular point, the universe may reach a maximum density and then bounce. This is often called the Big Bounce. In this picture, there may have been a contracting universe before the hot expanding phase we usually call the Big Bang. As that earlier universe contracted, its density increased. But instead of continuing into a singularity, quantum gravitational effects became dominant. Gravity, in this extreme regime, may have effectively changed character. The collapse stopped, reversed, and became expansion. The Big Bang in this model is not the absolute beginning, it is the transition from contraction to expansion. It is important not to picture this too mechanically. The universe is not a rubber ball bouncing on a floor. There is no outside surface, no cosmic trampoline, and no larger room in which the whole universe is dramatically flung upward again. The bounce is a change in the scale and geometry of the universe itself. It is space-time passing through an extreme quantum gravitational state. The appeal of this idea is clear. It replaces the classical singularity with a physical process. It gives a possible meaning to the phrase before the Big Bang. It suggests that the earliest boundary in general relativity may not be the end of reality, but the place where a deeper quantum description becomes necessary. In loop quantum cosmology, the universe before the bounce is not necessarily identical to the universe after it. The bounce may carry some information from the contracting phase into the expanding phase, but exactly how this works depends on the model. Some versions explore whether patterns from the pre-bounce universe could leave subtle traces in the fluctuations that later became cosmic structure. That is where observation becomes important. A scientific model of the early universe cannot survive on elegance alone. It has to connect somehow to evidence. The challenge is that the bounce, if it happened, would have occurred under conditions far beyond direct experiment. We cannot watch the universe bounce. We cannot build a laboratory version of the entire cosmos, press a large red button, and politely ask spacetime to do it again. But scientists can look for possible signatures. One place to search is in primordial fluctuations, the tiny early variations that later shape the cosmic microwave background and the large-scale structure of galaxies. If a bounce occurred before the hot expanding phase, it might have influenced the pattern of these fluctuations. It could, in principle, leave subtle imprints in the larger-scale features of the cosmic microwave background, or in the way early density variations were distributed. The difficulty is that these signals are extremely subtle, and many different early universe models can produce similar effects. Observations of the cosmic microwave background are powerful, especially from missions such as the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the European Space Agency's Planck spacecraft. But no decisive evidence has confirmed loop quantum cosmology as the correct description of the beginning, so the Big Bounce remains a serious possibility within a specific theoretical framework, not an established fact. This distinction matters. It is tempting to hear the phrase quantum gravity and imagine that it automatically solves the beginning of the universe. But physics is rarely that generous. Loop quantum cosmology is mathematically motivated and scientifically interesting, but it depends on ideas from loop quantum gravity, and loop quantum gravity itself has not yet been confirmed as the final theory of quantum spacetime. That does not make it worthless. Far from it. It makes it one of the disciplined attempts to explore what might lie beyond the breakdown of classical general relativity. It offers a way to replace infinity with a transition. It suggests that the universe may have a history before the hot, dense, expanding phase. It gives scientists a language for discussing a possible before without simply inventing one, but it must remain in its proper place on the confidence ladder. The hot Big Bang model is strongly supported by observations. The expansion of the universe, the cosmic microwave background, the abundance of light elements, and the growth of large-scale structure all point toward an early hot dense phase. Loop quantum cosmology goes deeper than that. It asks what might have happened before the conditions that are already well supported by evidence. That means it lives closer to the edge of known physics. And yet, that edge is exactly where the question of before belongs. If space-time is smooth all the way down, then general relativity seems to lead toward a singularity. But if space-time has quantum properties, then the singularity may be replaced by something else. A bounce is one of the clearest possibilities. In that case, there may have been a before the Big Bang, not as a vague philosophical suggestion, but as a contracting phase described by a particular form of quantum gravity. The universe may have passed through a deep, dense quantum bridge from one era to another, or it may not have. That is the honest balance. Loop quantum cosmology does not prove that the universe bounced. It shows that, if a certain approach to quantum gravity is right, the beginning may not be a beginning at all. It may be the turning point of a much larger story, where the universe did not emerge from a singular edge, but passed through one of the strangest transitions physics has ever imagined. One of the strangest answers to the question of before comes from Roger Penrose, the British mathematical physicist known for deep work on black holes, space-time, general relativity, and the large-scale structure of the universe. Penrose proposed an idea called conformal cyclic cosmology. It is a serious scientific proposal, but also a highly unusual one. It does not picture the Big Bang as the beginning of everything in a simple one-time event. Instead, it suggests that what we call our Big Bang may have been connected to the remote future of a previous cosmic era. In this view, the universe may pass through vast chapters called aeons. Each aeon begins with something like a Big Bang, and then expands for an unimaginably long time. Stars form, galaxies gather, black holes grow. Eventually, over timescales far beyond ordinary astronomical imagination, stars burn out, galaxies fade, and black holes slowly evaporate through Hawking radiation, the process named after Stephen Hawking. The far future in this picture becomes extremely cold, empty, and spread out. It is not empty in the everyday sense because radiation may remain, but massive structures, massive particles, and familiar clocks lose their importance. The universe becomes dominated by radiation, and by particles moving at the speed of light, where ordinary ideas of size and duration become less meaningful. This is where Penrose's idea becomes truly unusual. In physics, conformal geometry is concerned with shapes and angles while allowing distances to be stretched or compressed. Penrose suggested that if the far future of one eon contains no meaningful mass scale, then that enormously expanded future might be mathematically related to the compressed beginning of another aeon. In other words, the infinitely stretched future of one universe could be transformed, through a particular mathematical description, into the Big Bang of the next. That is not a simple bounce. In a bouncing universe, the cosmos contracts, reaches an extreme dense state, and then expands again. There is a clear image of collapse followed by expansion, even if the physics is very difficult. Penrose's conformal cyclic cosmology is different. It does not require the universe to contract back down. It imagines an ever-expanding universe whose far future can be reinterpreted under special conditions as the beginning of a new cosmic era. This is why it can feel so counterintuitive. The end does not crash into the beginning. The far future becomes, in a mathematical sense, like a new beginning. It is a little like saying that if the universe becomes stretched out enough, cold enough, and empty enough of meaningful mass, then the difference between the extremely large and the extremely small changes character. That is not meant as a casual visual picture. It is a statement about the geometry of space-time and the role of scale. Still, as a guiding image, it gives the idea its quiet strangeness. The universe does not bounce like a ball. It fades into a condition that may be mathematically joined to another beginning. Penrose's proposal is controversial. It is not the standard model of cosmology. Most cosmologists do not treat it as the established explanation of the Big Bang. The standard picture remains the hot Big Bang model, often combined with cosmic inflation, dark matter, dark energy, and the measured evidence of the cosmic microwave background and large-scale structure. But conformal cyclic cosmology is worth discussing because it addresses the question of before directly. It does not merely ask what happened a moment before the Big Bang, it imagines that there may have been an entire previous cosmic history before our own. Another aeon, with its own long evolution, its own galaxies, its own black holes, and its own remote ending. Penrose and collaborators have argued that there may be possible observational traces of previous aeons in the cosmic microwave background. One kind of claimed signature involves circular patterns or low-variance rings. Another involves possible regions sometimes called Hawking points, which are suggested to be faint traces of energy released by evaporating supermassive black holes in a previous arceon. These claims are debated. They are not considered settled evidence. Many scientists argue that the patterns identified may be statistical features, noise, foreground contamination, or results that do not clearly rise above what might appear in standard cosmology. The cosmic microwave background is an incredibly rich and delicate source of information, but it's also easy to overread if one is not careful. The universe has a habit of offering patterns, and the human mind has a habit of wanting those patterns to be messages. So the correct tone is caution. Conformal cyclic cosmology is not nonsense, but it is not confirmed. It is mathematically interesting, physically bold, and connected to real questions about space-time, entropy, mass, radiation, and the deep future of the universe. But it remains outside the mainstream standard model, and its proposed observational signatures remain disputed. Compared with inflation, Penrose's model tells a very different story. Inflation suggests that our hot Big Bang phase may have followed a very early rapid expansion. Eternal inflation may even suggest that our observable universe is one region among many. Bouncing cosmology suggests that the Big Bang may have followed a previous contraction. Loop quantum cosmology suggests that quantum geometry might replace the singularity with a bounce. Penrose's conformal cyclic cosmology offers another route entirely. It says that before our Big Bang there may not have been a contracting universe or a local inflationary background, but the unimaginably distant future of a previous universe. That gives the word before a grander and stranger meaning. It is not just a hidden moment tucked behind the first second. It is a whole cosmic era, stretched across timescales so vast that ordinary imagination simply gives up, makes a cup of tea, and leaves the mathematics to someone else. Whether this is true remains unknown, but it reminds us how open the deepest boundary still is. The Big Bang may have been an absolute beginning. It may have been a transition. It may have been the end of something else, rewritten as the start of everything we can see. And if Penrose is right, then the universe before this one was not just a prelude. It was an entire aeon, fading so completely that its final whisper may have become our first light. Cosmology can sometimes sound as though it is made from imagination, because its questions are so enormous. It speaks about the beginning of the universe, the shape of space, the first light, invisible matter, dark energy, and possible histories before the hot Big Bang. It asks what happened when no stars existed, when atoms had not yet formed, and when the universe was so dense that ordinary pictures fail almost immediately. It is understandable if part of the mind listens to all of that and quietly wonders whether cosmologists are simply being allowed too much coffee. But modern cosmology is not pure speculation. Its best models are tested against real observations. They are compared with galaxy surveys, the cosmic microwave background, primordial element abundances, gravitational lensing, and the expansion history of the universe. A cosmological model has to do more than sound elegant. It has to explain what telescopes, satellites, detectors, and careful measurements actually find. This is why the hot Big Bang model is so strong. It does not rest on one dramatic claim. It is supported by different kinds of evidence that fit together. galaxies show the expansion of space. The cosmic microwave background shows the universe's ancient thermal afterglow. The abundance of hydrogen, helium, and deuterium matches predictions from early nuclear reactions. The distribution of galaxies shows how tiny early fluctuations grew into vast cosmic structure. Each clue is different, but the larger pattern is consistent. Galaxy surveys are one of the ways scientists study that pattern. The Sloan Digital Sky Survey, based at Apache Point Observatory in New Mexico, has mapped millions of galaxies and quasars, helping reveal the large-scale structure of the universe. Instead of galaxies being scattered randomly like glitter thrown by someone with alarming enthusiasm, they form a cosmic web. Filaments, clusters, walls, and enormous voids. The European Space Agency's Euclid mission is designed to study dark energy, dark matter, and the geometry of the universe by measuring the shapes, distances, and distribution of galaxies across cosmic time. The Vera C. Rubin Observatory in Chile is expected to repeatedly scan the sky, building a deep moving map of the universe and helping scientists study dark matter, dark energy, supernova, asteroids, and many changing objects in the night sky. The James Webb Space Telescope has added another powerful window. It observes infrared light, allowing it to study some of the earliest galaxies in greater detail than before. Webb has revealed that galaxies in the young universe can be surprisingly bright, complex, and mature-looking. This has made scientists refine models of early galaxy formation. But it has not overturned the Big Bang model itself. That distinction matters. Discovering that early galaxies formed quickly does not mean the universe was never hot and dense. It means the processes that built the first galaxies may have been more efficient, varied, or complicated than some earlier models expected. Science often works this way. A new observation does not always destroy the main framework. Sometimes it sharpens the details, tidies the assumptions, and makes theorists stare thoughtfully at their computers for longer than planned. Another major clue comes from baryon acoustic oscillations. These are large-scale fossil patterns in the distribution of galaxies. In the early universe, before atoms formed, ordinary matter and radiation were joined in a hot plasma. Sound waves travelled through this plasma, creating patterns of slightly higher and lower density. When the universe cooled enough for light to travel freely, those waves effectively left an imprint. Billions of years later, that imprint can still be seen as a preferred scale in the spacing of galaxies. Baryon acoustic oscillations give scientists a kind of standard ruler for measuring cosmic expansion. They help trace how the expansion rate of the universe has changed over time, and they provide another test of the standard cosmological model. They connect the early hot plasma to the modern arrangement of galaxies, which is a remarkable bridge between the young universe and the universe we observe today. Gravitational lensing gives another line of evidence. According to general relativity, mass-curved spacetime and curved spacetime bends the path of light. When light from distant galaxies passes near massive clusters or large concentrations of dark matter, it can be distorted, magnified, or bent into arcs. By studying this lensing, scientists can map matter, including dark matter, even when that matter gives off no light of its own. Then there are gravitational waves. Gravitational waves are ripples in space-time, predicted by Albert Einstein's general theory of relativity and directly detected by the Laser Interferometer Gravitational Wave Observatory in 2015. The gravitational waves detected so far have come from events such as merging black holes and neutron stars, but in principle, gravitational waves could also carry information from extremely early cosmic events, perhaps from inflation or other violent processes in the young universe. This is especially exciting because gravitational waves might travel from periods earlier than the release of the cosmic microwave background. Light from before the universe became transparent cannot reach us directly in the same way, because the early plasma scattered it. But gravitational waves interact far more weakly, and could, in theory, preserve clues from much earlier times. However, primordial gravitational waves have not yet been definitively detected. Experiments such as the background imaging of Cosmic Extragalactic Polarization Project, known as BICEP, and the Keck Array have searched for subtle patterns in the polarization of the cosmic microwave background. In particular, scientists look for a twisting pattern called B-mode polarization, which could be a signature of primordial gravitational waves from inflation. The difficulty is that the Milky Way contains dust, and that dust can also produce polarized microwave signals. Separating a faint signal from the early universe from foreground emission inside our own galaxy is extremely difficult. Earlier claims of possible detection became more cautious once the role of galactic dust was better understood. This is not embarrassing. It is science doing the careful version of checking whether the mysterious noise is a cosmic message or just something much closer to home. All of this matters for the question of before the Big Bang. A beautiful idea is not enough. A mathematical model is not enough. Any scientific answer about what came before, or whether before even applies, must eventually connect to observable traces. It must explain something in the universe we can measure. It must leave a pattern in ancient light, galaxy structure, gravitational waves, element abundances, or some other physical clue. That is the difference between disciplined cosmology and pure storytelling. The universe may have had a prior phase. It may have bounced. It may have emerged through a quantum process. It may have passed through inflation before the hot Big Bang. Or the word before may fail near the origin. But for these possibilities to become more than elegant speculation, they must touch evidence. The early universe is not silent. It has left light, elements, ripples, galaxies, lensing patterns, and expanding space. But the closer we move toward the first boundary, the fainter the clues become. Science can follow them a long way back. Beyond that, it must proceed carefully, with imagination in one hand and measurement in the other. The question was, very before sounds simple until we notice that the word before is doing an enormous amount of work. In everyday conversation, before usually means an earlier moment. Before dinner, there was cooking. Before rain, there were clouds. Before a message was sent, someone stared at it for far too long, changed one word, changed it back, and then sent it anyway. The meaning feels obvious because ordinary life happens inside time. Events follow other events, causes come before effects. Memories point backward, plans point forward, and the present keeps slipping quietly between them. So when people ask whether there was a before the Big Bang, the everyday meaning is usually clear. They're asking whether something happened earlier. Was there empty space? Was there another universe? Was there a previous cycle? Was there a cause, a trigger, a condition, or some hidden stage before the hot expanding universe began? But the same question can mean different things in physics, philosophy, theology, and ordinary language. And unless those meanings are kept separate, the discussion can become confusing very quickly. Physics asks a particular kind of question. It asks what models can describe observations, make predictions, and connect with measurable reality. A physical theory should explain what telescopes see, what particles do, what radiation reveals, and what mathematical laws imply under clearly stated assumptions. In cosmology, physics asks how the universe expanded, how the cosmic microwave background formed, why light elements have the abundances they do, how galaxies grew, and what kinds of early universe models could leave observable traces. Philosophy can ask broader questions. It can ask what it means for something to exist at all. It can ask what causation means, if time itself has a beginning or a boundary. It can ask whether every explanation needs a prior explanation, or whether some facts are basic. It can ask why there is something rather than nothing. These are not foolish questions, they are deep questions. But they are not always answered in the same way that physics answers questions about redshift, radiation, and nuclear reactions. Theology may ask the question in still another way, often connecting cosmic origin to creation, purpose, dependence, or the relationship between the universe and a deeper reality beyond it. Everyday conversation may blend all of these together without noticing. One person may mean, what physical state came earlier? Another may mean, why does anything exist at all? Another may mean, did the universe require a creator? Another may simply be imagining a kind of cosmic waiting room, preferably one with very comfortable chairs before everything began. This is why the Big Bang is sometimes pulled into arguments that it does not actually settle by itself. The Big Bang model does not automatically prove creation from absolute nothing. It also does not automatically rule out a prior state, a deeper law, a bounce, an inflationary background, or some other kind of origin. The model tells us, with strong evidence, that the observable universe was once much hotter, denser, smoother, and more compressed than it is now. It tells us that space has expanded, that ancient radiation fills the sky, that hydrogen and helium formed in the early universe, and that tiny early variations grew into cosmic structure. But that is not the same as a complete answer to why there is a universe at all. Much of the confusion comes from the word nothing. In ordinary speech, nothing can mean an empty room. But an empty room is not really nothing. It has space, it has time, it has walls, air, temperature, and probably a suspiciously small amount of dust that nobody wants to take responsibility for. Even if all the air were removed, the room would still contain space and physical fields. It would still be part of the universe. Empty space is not absolute nothingness. In modern physics, empty space can have structure. It can contain quantum fields. It can have a vacuum state. It can be affected by gravity. It can expand. It can curve. It can possess measurable properties. So when physics talks about a vacuum, it is not talking about nothing in the deepest philosophical sense. A quantum vacuum is even subtler. It is the lowest energy state of quantum fields, but it is not a blank absence of reality. Quantum fields still exist. Physical laws still apply. Fluctuations and probabilities still belong to the description. Calling this nothing can be misleading if the listener imagines absolute non-existence. Then there is no classical space-time. Some quantum cosmology models try to describe the universe emerging from a state where ordinary space and ordinary time are not present. This is closer to what some physicists mean when they speak carefully about a universe from nothing. But even here the word nothing is technical. There may still be mathematical laws, a quantum state, boundary conditions, or a deeper framework in which the description is being made. Philosophical nothingness is more radical. It means no space, no time, no matter, no energy, no fields, no laws, no possibilities, no hidden structure, and no background from which anything could emerge. Physics does not easily speak about that kind of nothing, because physics normally works by describing some structure, rule, state, relation, or measurable consequence. This does not make physics weak. It makes physics honest about its domain. A scientific model may explain how one physical state leads to another. It may describe how an inflating state becomes a hot Big Bang universe, how a contracting universe bounces into expansion, how quantum geometry replaces a singularity, or how a no-boundary proposal changes the meaning of an earliest time. But even if such a model succeeded, one could still ask why those laws existed, why that quantum state was possible, or why there is any framework at all. That next question may be partly philosophical. It may not be answerable by the same tools used to measure the cosmic microwave background or map galaxies. A telescope can reveal ancient light. It cannot by itself tell us why reality is possible. This boundary between physics and philosophy is not a flaw in cosmology. It is a sign of intellectual honesty. Cosmology has turned many questions that once seemed unreachable into real scientific investigations. The age of the universe, the expansion of space, the early abundance of elements, and the afterglow of the hot early universe are no longer only matters of speculation. They are measured, tested, argued over, refined, and improved. But the deepest version of the question remains delicate. Was there a before? In one sense, physics may be able to answer. It may find evidence for a prior contracting phase, an inflationary state, a quantum transition, or some other pre-Big Bang condition. In another sense, the word before may fail if time itself is part of what begins or changes near the origin. And in yet another sense, the question may be asking why there is any reality at all, which reaches beyond current cosmology into philosophy and perhaps theology. So the careful answer is that before is not one question. It is a doorway into several questions, each with its own rules. The Big Bang tells us that the universe has a hot, dense early history. Physics can trace that history with remarkable power. But when we ask what lies behind it, we must listen closely to the words we're using. Before may mean an earlier physical phase. It may mean a limit where time loses its ordinary meaning, or it may mean the deepest question of existence itself. And at that depth, the mystery is not only about the universe, it is also about the language we use when we try to stand at the edge of time and ask what came before the edge. So was there a before the Big Bang? The most accurate answer is careful, and perhaps a little less dramatic than the question wants. The hot Big Bang almost certainly happened. The evidence that the universe was once in an extremely hot, dense, expanding state is very strong. But science does not yet know whether that state was the absolute beginning of everything. That distinction is the key. The Big Bang is not a wild guess about how something appeared from nothing. It is a physical model supported by several independent lines of evidence. The universe is expanding. Distant galaxies generally show redshift, meaning their light has been stretched as space itself has expanded. The cosmic microwave background fills the sky as the cooled afterglow of the early universe, released when the cosmos became transparent around 380,000 years after the hot beginning. The abundance of light elements, especially hydrogen and helium, matches what nuclear physics predicts from the first few minutes of cosmic history. And the large-scale structure of galaxies, clusters, filaments, and voids grew from tiny early fluctuations that we can still see faintly written into ancient light. These clues do not all come from the same place. They come from galaxy surveys, radio astronomy, nuclear physics, cosmic background measurements, gravitational lensing, and the study of structure across enormous distances. That is why the hot Big Bang model is so powerful. It is not balanced on one fragile observation. It is supported by a whole web of evidence, each strand strengthening the others. So if the question is, did the universe really pass through a hot, dense early phase? The answer is yes, as far as modern cosmology can tell. That part is not just a poetic image or a convenient story. It is the foundation of our best scientific picture of cosmic history. But if the question is, was that hot, dense phase the absolute beginning of all reality, the answer becomes much less certain. This is where the word before starts to shift under our feet. In ordinary life, before means an earlier time. Before a tree, there was a seed. Before a star, there was a cloud of gas. Before someone asks a very large cosmological question, there is usually a brief moment when they could have chosen something easier, but heroically did not. The mind wants the Big Bang to work the same way. Here is the event, so what came earlier? Yet the Big Bang is not an event inside a larger, already familiar space and time. It is tied to the history of space and time themselves. If time is part of the physical structure of the universe, then asking what happened before the universe may not always mean what it seems to mean. There may not be an ordinary, earlier moment in which something else was happening. Or there may be, but only if the correct deeper theory allows it. Different scientific models give different possibilities. In the Hartle-Hawking no-boundary proposal developed by James Hartle and Stephen Hawking, the earliest universe may be finite but without a sharp beginning in ordinary time. Near the boundary, time may behave more like a spatial dimension, so asking what happened before becomes like asking what lies north of the North Pole. The question is understandable, but the direction may stop applying. In Alexander Vilenkin's tunneling proposal, the universe may emerge through a quantum transition from a state with no classical space-time. This is sometimes described as tunneling from nothing, but that word nothing must be treated carefully. It does not simply mean empty space. It means no ordinary space and no ordinary time in the classical sense. In this kind of model, the universe may have an origin without a normal before. Eternal inflation offers another possibility. If inflation continued in some regions while ending in others, then our observable universe might be one region where inflation stopped and a hot Big Bang phase began. In that picture, the Big Bang was real, but it may have been a local beginning rather than the beginning of all reality. There could have been an inflating background before our hot Big Bang, although such regions may be far beyond observation. Bouncing cosmologies give a more direct meaning to before. In these models, the hot expanding universe may have been preceded by a contracting phase. The universe shrinks, reaches an extreme dense state, and then transitions into expansion. The Big Bang becomes a bounce, not an absolute first instant. This idea is scientifically appealing because it avoids a classical singularity and allows time to extend earlier, but it still faces the challenge of making testable predictions that match what we observe. Loop quantum cosmology offers a specific version of this kind of possibility. Based on ideas from loop quantum gravity, it suggests that if spacetime has quantum properties at extremely small scales, then the classical singularity may be replaced by a big bounce. Abhay Ashtekar and Martin Bodgerwald are among the important figures connected with this approach. The idea is mathematically serious, but it has not been proven as the final description of the universe. Roger Penrose's conformal cyclic cosmology gives yet another strange answer. It suggests that the remote future of one cosmic aeon may be mathematically connected to the Big Bang of the next. In that model, before our Big Bang there may not have been a contraction, or a local inflationary state, but an entire previous universe fading into a condition dominated by radiation and stripped of meaningful scale. It is a bold and controversial proposal, with claimed possible signatures in the cosmic microwave background, but those claims remain debated. So the honest answer is not one answer. It depends on which deeper theory, if any, turns out to be correct. There is a hierarchy of confidence here, and it matters. The hot, dense, early universe is strongly supported. Cosmic expansion, the cosmic microwave background, light element abundances, and large-scale structure make that case very powerfully. Inflation is plausible, influential, and widely studied, and it explains several important features of the observed universe, but its exact mechanism is not fully settled. Specific models about what came before the Big Bang, including no boundary proposals, tunneling models, eternal inflation, bouncing cosmologies, loop quantum cosmology, and conformal cyclic cosmology, remain speculative. Speculative does not mean silly. It means not yet confirmed. These ideas are not random guesses thrown into the dark. They are attempts to extend physics toward a boundary where general relativity, quantum theory, particle physics, and cosmology all meet. But until they connect more decisively with observation, they remain possibilities rather than conclusions. That is not a failure. In fact, it is remarkable that the question can be studied scientifically at all. For most of human history, asking what happened before the universe belonged almost entirely to myth, philosophy, and theology. Modern cosmology has not solved it completely, but it has changed the nature of the question. It has shown that the universe has a measurable past. It has found ancient light. It has measured expansion. It has calculated the formation of the first light elements. It has mapped the tiny ripples that became galaxies. Science has not reached the final page, but it has read astonishingly far back into the book. So, was there a before? There may have been. If a bouncing model, an inflationary prehistory, a cyclic aeon, or some deeper quantum gravitational theory is correct, then the hot Big Bang was not the absolute beginning. It was a transition, a local beginning, or the opening of the cosmic era we can observe. Or there may not have been a before in the ordinary sense. if time itself emerged with the universe, or if the earliest boundary is not a moment inside time, then the question may dissolve at the edge. Not because it is foolish, but because the word before was built for a universe already running. Perhaps the Big Bang is not a wall. A wall suggests a hard ending, a final barrier, a place where explanation simply stops. It may be more like a horizon. A horizon is not the end of the world. It is the point beyond which, from where we stand, our view begins to fade. The Big Bang may be the horizon behind the beginning, not necessarily the end of reality, but the place where current evidence grows faint, current theory becomes uncertain, and the deepest mystery of time awaits quietly beyond the light.